Right now, 2.5 million light-years away, something unimaginable is racing toward us. It contains over 1 trillion stars, enough to outshine our entire galaxy. It harbors black holes so massive they could swallow our solar system without a trace. And it's moving at 250,000 miles per hour on a direct collision course with everything we've ever known. But for most of human history, we didn't even know it existed. What you're looking at when you see the Andromeda Galaxy is light that began its journey toward Earth before our species learned to walk upright. That light has traveled across the cosmic void for over 2 million years, carrying with it secrets that could rewrite everything we think we know about life, physics, and our place in the universe. Yet just over a century ago, the brightest minds on Earth looked directly at this cosmic colossus and saw nothing more than a faint smudge of light. They called it a nebula, assuming it was just another cloud of gas drifting within our own galaxy. They couldn't have been more wrong. Here's a thought experiment that puts this mistake into perspective. Imagine you're an ant living on a single leaf of a massive oak tree. From your perspective, that leaf is your entire world. You might notice other leaves nearby and assume they're all part of the same tree you're living on. Now imagine that what you thought was just another leaf on your tree is actually an entire forest on the other side of the continent. That's essentially what happened with Andromeda. We mistook an entire galaxy for a nearby gas cloud. But here's what makes this story even more remarkable. The light you see from Andromeda tonight left that galaxy when our ancestors were still sharing the African landscape with saber-toothed cats and giant ground sloths. If you could somehow send a message to Andromeda today, and they could send one back immediately, their response wouldn't reach Earth until long after our sun has exhausted its fuel and died. We are quite literally looking into deep history every time we observe this galaxy. The story of how we discovered Andromeda's true nature is one of the most dramatic reversals in scientific history. It's a tale of stubborn assumptions, revolutionary observations, and a universe that turned out to be so much larger and stranger than anyone had dared imagine. But more than that, it's the story of how a single discovery shattered our cosmic perspective and revealed that we live in a universe filled with galaxies beyond counting. To understand the magnitude of this revelation, you have to transport yourself back to the early 1900s and see the cosmos through the eyes of astronomers who believed they had it all figured out. Picture yourself in 1900, when the fastest mode of transportation was the steam train, when most people had never seen an electric light, and when the idea of powered flight was still considered fantasy by serious scientists. At that time, the prevailing view of the cosmos was simple and comforting. The Milky Way galaxy was everything. Every star you could see in the night sky, every wisp of cosmic gas, every celestial phenomenon was part of our home galaxy. The universe, in their minds, was perhaps 300,000 light-years across, and we were somewhere near its center. It was a cozy, comprehensible cosmos where humanity held a special place at the heart of creation. This wasn't ignorance. It was the result of careful observation and logical reasoning by some of history's most brilliant scientists. The evidence seemed clear. When they pointed their telescopes at the night sky, they could see individual stars throughout the Milky Way's disk. They could map globular clusters orbiting our galactic center. They could trace the bright band of stars that forms the visible edge of our galaxy's spiral arms. Everything fit neatly into a single, coherent picture. But think about how this would have felt to someone living in that era. The universe was a place where humans weren't just accidentally special, we seemed to occupy the central stage of the cosmic drama. Our galaxy was the only galaxy, making Earth not just a planet in a solar system, but a world in the only stellar system that mattered. It was a view that placed tremendous significance on every human action and thought. But there were problems with this view. Scattered across the sky, astronomers had catalogued hundreds of mysterious objects they called spiral nebulae. These weren't like the chaotic, irregular gas clouds they saw elsewhere in the galaxy. Instead, they had organized elegant structures that looked almost like pinwheels of light spinning slowly in space. Some showed clear spiral patterns, Others appeared more elliptical or irregular, but they all shared one troubling characteristic. They seemed to be moving away from us at incredible speeds. The most prominent of these spiral nebulae was the object we now call the Andromeda Galaxy. Even to the naked eye, it appeared as a faint, elongated patch of light in the constellation Andromeda. Through telescopes, it revealed a complex structure with dark lanes of what appeared to be dust, bright central regions, and extended arms that curved gracefully outward from the center. Here's a detail that most people don't know. You can actually see Andromeda with your naked eyes on a clear, dark night. It appears as a faint, fuzzy star, but what you're really seeing is the combined light of 1 trillion stars, so distant that they blur together into a single glow. Every photon that hits your retina has been traveling toward Earth since before our species existed. You are literally seeing ancient light with your own eyes. But here was the puzzle that kept astronomers awake at night. If these spiral nebulae were just gas clouds within our galaxy, why did they look so different from other nebulae? And why were so many of them moving away from us? The speeds were enormous, hundreds or even thousands of kilometers per second. For objects within our galaxy, such velocities seemed impossible. To put these speeds in perspective, imagine driving on a highway where every other car is traveling at 2 million miles per hour. That's roughly how fast these nebulae appeared to be moving compared to normal objects in our galaxy. Something was clearly very wrong with the picture, but no one could figure out what. Some astronomers began to suspect that these spiral nebulae might be something far more extraordinary. What if they weren't gas clouds at all, but entire galaxies like our own, so distant that their individual stars blurred together into a faint glow? It was a radical idea, one that would expand the known universe by millions of times. But it would also solve the mystery of why these objects looked so organized and why they were moving so fast. The idea of island universes wasn't entirely new. The philosopher Immanuel Kant had speculated about it in the 18th century, calling these distant objects island universes floating in the cosmic ocean. But speculation wasn't science. To prove that spiral nebulae were distant galaxies, astronomers would need to measure their distances with unprecedented precision. And that seemed impossible with the technology of the early 1900s. The problem was fundamental. How do you measure the distance to something so far away that you can't even see its individual stars? It's like trying to determine whether a distant light is a candle a mile away or a bonfire 50 miles away when all you can see is a faint glow on the horizon. Astronomers had developed clever techniques for measuring distances within our own galaxy, but these methods all required being able to identify specific types of stars or other objects whose brightness was well understood. If spiral nebulae were truly distant galaxies, their individual stars would be far too faint to study, like trying to make out individual people in a city when you're flying at 30,000 feet. This scientific impasse led to one of the most famous debates in astronomical history. In April 1920, the National Academy of Sciences organized a public discussion between two of America's leading astronomers, Harlow Shapley of Harvard College Observatory and Heber Curtis of Lick Observatory. The topic was the scale of the universe, but everyone knew the real question was whether spiral nebulae were distant galaxies or nearby gas clouds. Picture this scene. Two of the most respected scientists in America standing before an audience of their peers in Washington, D.C., about to engage in a debate that would literally determine the size of our universe. The stakes couldn't have been higher. If Shapley was right, humanity lived in a cozy universe perhaps 300,000 light-years across. If Curtis was correct, we inhabited a cosmos millions of times larger than anyone had dreamed possible. It was like two explorers arguing about whether they were standing in their backyard or on an uncharted continent, with the entire map of reality hanging in the balance. Shapley argued for the traditional view. He had recently completed groundbreaking work mapping the size and structure of the Milky Way, revealing it to be much larger than previously thought. His measurements suggested our galaxy was roughly 30,000 light-years across, making it a truly enormous structure. If the Milky Way was that big, Shapley reasoned, it could easily contain all the known spiral nebulae. There was no need to postulate the existence of other galaxies. Moreover, Shapley pointed to several pieces of evidence that seemed to support his position. Some spiral nebulae showed signs of rotation, but if they were distant galaxies, they would have to be spinning impossibly fast, so fast that they should tear themselves apart from centrifugal force. Others seemed to change brightness over time, but distant galaxies shouldn't vary noticeably over human timescales. Most convincing of all, a few spiral nebulae had been observed to produce nova explosions, sudden brightenings that appeared to be individual stars. If these nebulae were truly distant galaxies, such individual stars should be completely invisible. It's worth pausing here to appreciate just how reasonable Shapley's argument sounded. Imagine you're looking at what appears to be a candle flame in the distance. If someone told you it was actually a forest fire on the other side of the country, you'd be skeptical too. How could something so faint be so enormous and distant? Shapley was applying the same logical skepticism to the island universe hypothesis. Curtis, on the other hand, argued for the island universe hypothesis with the passion of someone who had seen something that others had missed. He acknowledged the problems with Shapley's objections, but offered alternative explanations that revealed his remarkable scientific intuition. The apparent rotation could be an illusion caused by the complex motions of gas and dust within the nebulae. The brightness variations might be due to supernovae, stellar explosions far more powerful than ordinary novae. As for the individual novae, Curtis suggested they might actually be entire star-forming regions, not individual stars at all. More importantly, Curtis had noticed something that troubled him deeply about the novae in spiral nebulae. On average, they appeared much fainter than novae observed in our own galaxy. If the spiral nebulae were nearby objects within the Milky Way, their novae should appear as bright as local ones. The fact that they were systematically dimmer suggested they were much farther away than Shapley believed. Here's an analogy that captures Curtis's reasoning. If you're looking at street lamps, the ones that appear dimmer are probably farther away. Curtis was applying the same logic to stellar explosions. The fainter ones were likely more distant. It seems obvious now, but it was revolutionary thinking at the time. Curtis also pointed to the peculiar distribution of spiral nebulae in the sky. They seemed to avoid the plane of the Milky Way, clustering instead near the galactic poles. If they were part of our galaxy, this distribution would be very strange. But if they were distant objects, it would make perfect sense. Dust in our galaxy's disk would obscure our view of distant spiral nebulae along the galactic plane, allowing us to see them clearly only when we looked up or down from the disk. Think of it like trying to see distant mountains while driving through a forest. When you look straight ahead through the trees, your view is blocked. But when you look up through a clearing in the canopy, you can see the peaks in the distance. Curtis realized that the same principle applied to spiral nebulae. We could only see them clearly when we looked out of our galaxy's dusty plane. But here's a detail that makes this story even more fascinating. Curtis was making these arguments based on photographic plates that took hours to expose and revealed details that were barely visible to the human eye. He was essentially arguing for a universe millions of times larger than anyone believed possible based on faint smudges on glass plates. The courage required to advocate for such a radical expansion of cosmic scale based on such subtle evidence is hard to imagine. The debate was a draw. Both men presented compelling arguments, but neither could provide definitive proof for their position. The question of the universe's scale would have to wait for better observations and new techniques. But the very fact that this debate occurred reveals something profound about the scientific process. Sometimes the most fundamental questions about reality can't be settled by clever arguments alone. They require new observations, new instruments, and often new ways of thinking about familiar phenomena. But the wait wouldn't be long. Just 4 years after the Great Debate, a young astronomer at Mount Wilson Observatory in California would make the observation that settled the question once and for all. Edwin Hubble was already recognized as one of the most skilled observers of his generation. He had access to the 100-inch Hooker telescope, then the largest and most powerful telescope in the world. More importantly, he had the patience and technical skill needed to push the instrument to its absolute limits. Here's what made Hubble special. Most astronomers of his era took a few photographs of an object and called it good enough. Hubble was different. He would return to the same object night after night, month after month, building up incredibly deep images that revealed details no one had ever seen before. He was like a detective gathering evidence piece by piece until the truth became undeniable. Hubble focused his attention on the Andromeda Nebula, the largest and brightest of the spiral nebulae. Night after night, he took long exposure photographs of the object, each one revealing fainter details than the last. He was looking for something specific: Cepheid variable stars. Cepheids were a special class of stars that had been discovered in our own galaxy just a few decades earlier. They were massive, luminous stars that pulsed regularly, growing brighter and dimmer in cycles that lasted days or weeks. But here was the key. There was a precise mathematical relationship between how long a Cepheid's pulsation cycle lasted and how luminous it actually was. The longer the period, the brighter the star. This period luminosity relationship, discovered by Henrietta Swan Leavitt at Harvard College Observatory, was one of astronomy's most powerful tools. If you could measure how fast a Cepheid pulsed, you could calculate its true brightness. And if you knew both its true brightness and how bright it appeared from Earth, you could calculate exactly how far away it was. It's like having a light bulb with known wattage. If you see it glowing dimly in the distance, you can calculate how far away it is based on how faint it appears. The dimmer it looks, the farther away it must be. Leavitt had essentially given astronomers a set of standard candles that could be used to measure cosmic distances. But here's a detail that reveals the human side of this cosmic discovery. Henrietta Leavitt was working as a computer at Harvard Observatory, one of several women who were hired to analyze photographic plates for a fraction of the salary paid to male astronomers. She made her groundbreaking discovery while doing routine measurements of variable stars, work that was considered mechanical and unimportant by the male astronomers of the time. Yet her discovery would provide the key to unlocking the true scale of the universe. The challenge was finding Cepheids in the Andromeda Nebula. If it was just a nearby gas cloud, as Shapley believed, any Cepheids within it should be easily visible. But if it was a distant galaxy, its Cepheids would be incredibly faint, pushing the limits of even the world's most powerful telescope. On the night of October 5, 1923, Hubble made the observation that would change everything. While examining his latest photographic plate of Andromeda, he noticed something that made his pulse quicken. In one of the nebula's spiral arms, he had captured the image of a star that appeared on some plates, but not others. It was a variable star, and its location was precisely noted in his observing log. Imagine the excitement Hubble must have felt in that moment. He was staring at a photographic plate, squinting through a magnifying glass in the dim light of the observatory when he spotted something that had never been seen before. This wasn't just another star, it was potentially the key to unlocking one of the universe's greatest mysteries. But here's a detail that makes Hubble's discovery even more remarkable. He initially thought he had found a nova, a stellar explosion. He actually wrote N for nova on the photographic plate. Only after weeks of additional observations did he realize that the star wasn't exploding. It was pulsating regularly like a Cepheid variable. He crossed out the N and wrote VAR for variable star. That crossed out letter N represents one of the most significant corrections in the history of science. Over the following weeks, Hubble continued to monitor this star, carefully measuring its brightness and timing its variations. The pattern that emerged was unmistakable. It was a Cepheid variable with a pulsation period of 31.4 days. Using Leavitt's period luminosity relationship, Hubble calculated that the star had an intrinsic luminosity roughly 7,000 times that of our Sun. But when Hubble compared this calculated brightness with how faint the star actually appeared in his photographs, the result was staggering. The star was so distant that its light had traveled for roughly 900,000 years to reach Earth. This single measurement placed the Andromeda Nebula far beyond the boundaries of our own galaxy. Actually, Hubble's first calculation underestimated the true distance by a factor of more than 2. Later refinements to the Cepheid distance scale would reveal that Andromeda is actually about 2.5 million light-years away. But even his initial measurement was sufficient to prove that Andromeda was not a nebula within our galaxy, but an entirely separate galaxy comparable in size to the Milky Way. Here's a way to visualize what Hubble had discovered. If our Milky Way galaxy were the size of a dinner plate, Andromeda would be another dinner plate sitting about 20 feet away. Suddenly, the universe wasn't a single plate sitting on a table. It was a vast warehouse filled with countless plates scattered throughout an enormous space. The implications were revolutionary. If Andromeda was a separate galaxy, then so were the other spiral nebulae scattered across the sky. The universe wasn't a single galaxy surrounded by empty space. It was filled with countless galaxies, each containing billions of stars, stretching out to distances that dwarfed anything previously imagined. Hubble announced his discovery at a meeting of the American Astronomical Society on December 30th, 1924. The reaction was immediate and profound. Henry Norris Russell, one of Princeton's most distinguished astronomers, called it the most outstanding discovery in astronomy since the time of Kepler. The size of the known universe had suddenly expanded by a factor of millions. But here's something most people don't realize: Hubble almost didn't make this discovery. In the weeks before his breakthrough observation, he had been growing frustrated with his search. The Cepheids in Andromeda were so faint that they appeared on only the very best photographic plates, taken on nights with perfect atmospheric conditions and no moonlight to interfere. The exposures had to be perfect. The tracking of the telescope had to be precise, and the development of the plates had to be done with extraordinary care. Many astronomers would have given up, but Hubble persisted, driven by an almost obsessive attention to detail that bordered on the compulsive. There's also a personal drama underlying this scientific breakthrough. Hubble was competing with other astronomers who were pursuing the same goal. Milton Humason, Hubble's observing partner at Mount Wilson, later recalled that they knew they were in a race against time and other observers. Every clear night was precious, every photographic plate potentially decisive. The pressure was enormous, and the stakes were nothing less than determining the true nature of the universe. But Hubble wasn't finished. Having established that Andromeda and other spiral nebulae were distant galaxies, he set out to measure their distances systematically. What he discovered would prove even more revolutionary than his initial finding. As Hubble measured the distances to more and more galaxies, he noticed something extraordinary. They were almost all moving away from us. The more distant the galaxy, the faster it appeared to be receding. This relationship, which became known as Hubble's law, provided the first evidence that the universe itself was expanding. Think about what this means for a moment. Hubble hadn't just discovered that other galaxies existed, he had stumbled upon evidence that the entire universe was growing larger. It's as if he had been studying what he thought were nearby islands, only to discover they were distant continents, and then realized that all the continents were drifting apart from each other. The discovery that we live in an expanding universe filled with billions of galaxies fundamentally transformed our understanding of cosmic history and structure. It laid the groundwork for the Big Bang theory and modern cosmology. It revealed that the universe had a beginning and suggested it might have an end. Most importantly for our story, it established that the Andromeda Galaxy was our nearest galactic neighbor, a cosmic twin separated from us by an almost unimaginable gulf of space and time. But even as astronomers celebrated this expansion of cosmic perspective, they realized they had barely begun to understand what they had discovered. If Andromeda was truly a galaxy like our own, what was it made of? How had it formed? What processes shaped its structure and powered its evolution? And perhaps most intriguingly, was it home to planets and possibly life beyond anything we had imagined? These questions would drive astronomical research for the next century. Every new telescope, every technological advance, every theoretical breakthrough would reveal new aspects of Andromeda's nature and deepen the mystery of what it meant to live in a universe filled with such magnificent structures. The measurement of Andromeda's distance also raised a troubling possibility that wouldn't be fully understood for decades. If galaxies were separate entities moving through space, what happened when they encountered each other? Could galaxies collide? And if so, what would be the consequences for any planets or civilizations they contained? These weren't just theoretical questions. As astronomers refined their measurements of Andromeda's motion, they discovered something that seemed to contradict Hubble's expanding universe. Unlike most other galaxies, which were moving away from us, Andromeda appeared to be approaching. Its light was shifted toward the blue end of the spectrum, indicating it was moving in our direction at roughly 110 kilometers per second. At first, this seemed like a small anomaly. The approach speed was modest compared to the recession velocities of distant galaxies. But as measurements became more precise, astronomers realized they were witnessing something unprecedented: two massive galaxies on a collision course. Here's a thought that should give you pause. Every second you've been listening to this story, Andromeda has moved about 70 miles closer to our galaxy. By the time you go to sleep tonight, it will be roughly 6 million miles closer than it was when you woke up this morning. The collision is still billions of years in the future, but it's as inevitable as sunrise. The Andromeda Galaxy, with its trillion stars and massive dark matter halo, was heading directly toward the Milky Way. The collision was still billions of years in the future, but it was inevitable. When it occurred, it would be the most dramatic event in our local cosmic neighborhood since the formation of the galaxies themselves. This realization added a new dimension to the study of Andromeda. It wasn't just our nearest galactic neighbor, it was our future. Understanding Andromeda meant understanding what would happen to our own galaxy, our solar system, and potentially our species in the distant future. But that collision is still billions of years away. Right now, Andromeda serves as a laboratory for understanding how galaxies work, a cosmic mirror that reflects the processes that shaped our own galactic home. Every detail of its structure tells a story about the forces that govern cosmic evolution. Every star within its borders represents a potential site for planet formation and possibly life. The journey from seeing Andromeda as a faint nebula to understanding it as a galaxy containing over 1 trillion stars represents one of the greatest expansions of human perspective in history. It revealed that our universe is far larger, more complex, and more magnificent than anyone had dared imagine. But it also raised profound questions about our place in this vast cosmic arena. If galaxies like Andromeda exist throughout the universe, each containing billions of stars and potentially trillions of planets, then the likelihood of life existing elsewhere becomes almost a certainty. The question is no longer whether life exists beyond Earth, but what forms it might take and whether we will ever be able to detect it across the cosmic distances that separate us from our galactic neighbors. But here's perhaps the most humbling realization. When we look at Andromeda today, we're seeing it as it was 2.5 million years ago. If there are civilizations in that galaxy, they could have risen and fallen, built great cities and explored their stellar neighborhood, perhaps even sent signals toward our galaxy, all without us knowing it. The light-carrying news of their achievements is still traveling through the cosmic void and won't reach us for another 2.5 million years. And here's an even more mind-bending thought. If beings in Andromeda are looking back at us right now with their own telescopes, they're seeing our galaxy as it was 2.5 million years ago, when early human ancestors were just beginning to walk upright on the African savanna. They have no idea that in the intervening time, one species on a small planet in our galaxy has developed the intelligence to study their home and predict its collision with ours. The discovery of Andromeda's true nature also marked the beginning of modern cosmology. Once astronomers accepted that the universe contained countless galaxies, they were forced to confront fundamental questions about cosmic origins, structure, and destiny. How did galaxies form in the early universe? What forces shaped their evolution? And what would happen to them in the far future as the universe continued to expand and cool? These questions led to some of the most important discoveries in 20th century science: dark matter, dark energy, black holes, cosmic microwave background radiation, and the Big Bang theory itself. Each of these discoveries deepened our understanding of Andromeda and its place in the cosmic web of structure that spans the observable universe. Today, nearly a century after Hubble's breakthrough observation, Andromeda continues to surprise us. Advanced telescopes have revealed details of its structure that would have been unimaginable to early 20th century astronomers. We can now see individual stars within its spiral arms, map the distribution of gas and dust throughout its disk, and even detect planets orbiting some of its stars. But, perhaps most remarkably, we've discovered that Andromeda is not the static, unchanging structure that early astronomers imagined. It's a dynamic, evolving system that has grown through countless interactions with smaller galaxies over billions of years. Its current structure preserves the history of these ancient collisions in the form of stellar streams, disturbed gas clouds, and unusual populations of stars. The galaxy we see today is the result of over 10 billion years of cosmic evolution. It has witnessed the birth and death of countless generations of stars, the formation and destruction of innumerable planetary systems, and possibly the rise and fall of civilizations we can only imagine. As we stand on the threshold of a new era in astronomy, with space-based telescopes of unprecedented power and ground-based facilities that can peer deeper into space than ever before, Andromeda continues to beckon us with mysteries yet unsolved. What secrets does it hold about the formation of the first stars and galaxies? What can it teach us about the nature of dark matter and dark energy? And perhaps most tantalizingly, could it be home to intelligent life that is even now studying our own galaxy and wondering, as we do, whether they are alone in the universe? The story of Andromeda began with a simple question: what is that faint smudge of light in the night sky? The answer transformed our understanding of the universe and our place within it. But in many ways, that story is just beginning. As we prepare to explore the galaxy's hidden depths and unravel its remaining mysteries, we're reminded that every answer we find opens the door to even more profound questions about the nature of reality itself. Now that we know Andromeda is a galaxy, the next question becomes almost overwhelming. What exactly are we looking at? The answer will challenge everything you think you know about matter, space, and the very fabric of reality itself. Because when astronomers finally began to measure Andromeda properly, they discovered something that shouldn't be. The galaxy we can see with our telescopes, brilliant and magnificent as it appears, represents less than 15% of what's actually there. The other 85% is completely invisible, made of a substance so mysterious that after nearly a century of intensive research, we still don't know what it is. And without this invisible component, the beautiful spiral galaxy we admire in photographs simply couldn't exist. But here's what might blow your mind. You can experience this mystery yourself. On any clear night, when you look up at Andromeda, you're seeing only a tiny fraction of what's actually there. The vast majority of the galaxy, more than 5 times as much matter as all the visible stars combined, is completely invisible to your eyes and to every telescope ever built. It's like looking at an iceberg and seeing only the small tip that pokes above the water, unaware that a massive structure lurks hidden beneath the surface. But let's start with what we can see, because even the visible portion of Andromeda defies comprehension. When you look at the most detailed images of this galaxy, you're seeing light from approximately 1 trillion individual stars. To put that number in perspective, if you could count 1 star every second without ever stopping, no breaks for sleep, food, or rest, it would take you over 30,000 years to count them all. And remember, that's counting non-stop at 1 per second for 30 millennia. Here's another way to grasp this number. If every star in Andromeda were a grain of sand, you would need roughly 20 million dump trucks to carry them all. Or think of it this way. If you lined up all of Andromeda's stars like cars in a traffic jam, the line would stretch for 20 billion miles, enough to reach from the Sun to Neptune and back again over 600 times. Each of those trillion stars is a nuclear furnace, converting hydrogen to helium in reactions so powerful they light up space for millions of light years in every direction. The total energy output of Andromeda is roughly 25 billion times that of our Sun. To put this in perspective, if you could somehow harness just 1% of the energy Andromeda produces in a single second, it would power all of human civilization for millions of years. But here's something that might surprise you. Despite containing 1 trillion stars, Andromeda is mostly empty space. If you could shrink it down so that each star was the size of a grain of sand, the galaxy would still be about 13,000 miles across. The distances between stars are so vast that if you were somehow transported to a random location within the galaxy, the night sky would likely look very similar to what we see from Earth, a scattering of distant points of light against the cosmic dark. The galaxy itself spans approximately 220,000 light-years from edge to edge, making it significantly larger than our own Milky Way. To cross Andromeda at the speed of light would take 220,000 years. To drive across it at highway speeds would take over 1.5 billion years, longer than complex life has existed on Earth. If you could fold space and somehow walk across the galaxy taking 1 step per second, it would take you over 7 trillion years to reach the other side. But size isn't the only way Andromeda dwarfs our home galaxy. Its total mass is estimated at roughly 1.5 trillion times that of our Sun, making it the most massive galaxy in our local cosmic neighborhood. When it eventually collides with the Milky Way in about 4.5 billion years, Andromeda will be the dominant partner in that cosmic merger. The structure of Andromeda follows the classic pattern of a spiral galaxy, but with complexities that have puzzled astronomers for decades. At its heart lies a dense central bulge, a roughly spherical region packed with older, redder stars. This bulge extends about 5,000 light-years from the galactic center and contains roughly 140 billion stars, more than the entire stellar population of some smaller galaxies. Think about that for a moment. The central bulge of Andromeda alone contains more stars than many entire galaxies. If you could somehow extract just this central region and place it in isolation, it would still be one of the largest galaxies in our local cosmic group. It's like discovering that what you thought was a large city actually has a downtown core that's bigger than most entire countries. Surrounding the central bulge is Andromeda's disk, a flattened structure that contains the galaxy's magnificent spiral arms. These arms aren't solid structures like the spokes of a wheel. Instead, they're density waves, regions where stars and gas are temporarily compressed as they orbit the galactic center. As material moves through these density waves, it gets compressed, triggering bursts of star formation that light up the spiral arms with young blue stars. But here's where Andromeda gets interesting. It doesn't have the two-armed spiral structure you might expect. Instead, astronomers have identified what appears to be a more complex pattern, possibly the result of past interactions with smaller galaxies. The spiral arms aren't perfectly symmetric, and there are regions where the expected pattern seems disrupted or distorted. This asymmetry tells a story of violence and disruption in Andromeda's past. Galaxies aren't the serene, unchanging structures they appear to be in photographs. They're dynamic systems that grow and evolve over billions of years through interactions, mergers, and internal processes we're only beginning to understand. Imagine if you could watch Andromeda's evolution in time-lapse, with each second representing 1,000,000 years. You would see it as a churning dynamic system with spiral arms forming and dissolving, gas clouds collapsing to birth, new stars and smaller galaxies occasionally crashing into the main structure like cosmic pinballs. The stately spiral galaxy we see today is just a single frame in a billions-year movie of cosmic evolution. Beyond the visible disk lies Andromeda's extended halo, a roughly spherical region that stretches far beyond the bright spiral arms. This halo contains globular clusters, ancient collections of stars that formed in the early universe, as well as streams of stars that are the remnants of smaller galaxies that Andromeda has consumed over its lifetime. The halo is also home to something far more mysterious, the bulk of Andromeda's dark matter. This invisible substance extends much farther than the visible galaxy, forming a massive cocoon that may stretch for hundreds of thousands of light years in every direction. If you could somehow see dark matter, Andromeda would appear as a vast, ghostly sphere with the visible galaxy floating like a small bright disk at its center. The discovery of dark matter in Andromeda and other galaxies represents one of the most profound mysteries in modern science. The story begins with a simple observation that completely overthrew our understanding of what galaxies are made of. When astronomers measure how far stars orbit around Andromeda's center, they find something that doesn't make sense according to our understanding of gravity and physics. In our solar system, planets farther from the Sun orbit more slowly than those closer in. Mercury whips around the Sun in just 88 days, while distant Neptune takes one orbit to complete one orbit. This relationship between distance and orbital speed follows from Newton's laws of gravity and motion, and it's been verified countless times in our solar system and in other star systems. This makes perfect physical sense. The Sun contains 99.8% of the mass in our solar system, so the farther you get from this central mass concentration, the weaker the gravitational pull becomes, and the slower planets need to move to maintain stable orbits. It's like a ball on a string. The longer the string, the slower it needs to spin to maintain the same centripetal force. Galaxies should work the same way. Stars near the galactic center, where most of the mass is concentrated, should orbit faster than stars in the outer regions. But when astronomers measured the orbital speeds of stars throughout Andromeda, they found something completely unexpected and seemingly Stars in the outer regions of the galaxy were moving just as fast as those closer to the center. In some cases, the outer stars were actually moving faster than inner ones. According to everything we know about gravity, this should be impossible. The outer stars should be moving so slowly that they'd barely be bound to the galaxy at all, if they were bound at all. Here's an analogy to help you understand how shocking this discovery was. Imagine you're watching a merry-go-round where the horses on the outer edge are spinning around just as fast as those near the center. This would violate everything we know about rotational motion. The outer horses should be moving much more slowly, or they would fly off the ride entirely. There were only two possible explanations for this observation. Either our understanding of gravity was fundamentally wrong, meaning we would need to abandon Newton's laws and Einstein's general relativity, theories that had been tested countless times and never found wanting, or there was much more mass in Andromeda than we could see. The first option would require throwing out the foundations of physics. The second option required accepting that most of the universe was made of something we had never detected directly. Most astronomers chose the second option, and the concept of dark matter was born. According to this hypothesis, every galaxy is surrounded by a vast halo of invisible matter that provides the extra gravity needed to keep outer stars moving at their observed speeds. This dark matter doesn't emit, reflect, or absorb light, making it completely invisible to our telescopes. We can only detect it through its gravitational effects on the matter we can see. But here's what's truly staggering. In Andromeda's case, the amount of dark matter required is enormous. For every kilogram of normal matter in the galaxy, every star, planet, gas cloud, and dust grain, there must be roughly 5 kilograms of dark matter. The stars, planets, gas, and dust that make up everything we can see represent less than 20% of the galaxy's total mass. The other 80% is something we don't understand. Think about what this means. When you look at Andromeda, you're seeing less than 1/5 of what's actually there. It's like looking at a city at night and seeing only the lit windows, unaware that the vast majority of the buildings are completely dark and invisible. But what could dark matter actually be? Over the decades since its discovery, scientists have proposed numerous candidates, and the possibilities range from merely exotic to completely mind-bending. Some have suggested it might be composed of exotic subatomic particles that rarely interact with normal matter. These hypothetical particles, with names like WIMPs, weakly interacting massive particles or axions, would have been created in the early universe and would still permeate space today. Others have proposed more exotic possibilities. Perhaps dark matter exists in extra dimensions we can't perceive directly, like shadows cast into our three-dimensional world from higher dimensional spaces. Maybe it's composed of primordial black holes formed in the first moments after the Big Bang, each one microscopic but collectively accounting for the missing mass. Or it could be something even stranger, like particles that exist in a dark sector of physics with its own forces and interactions that mirror but don't directly affect our own. Here's a thought experiment that illustrates just how alien dark matter might be. Imagine there's an entire parallel universe occupying the same space as our own, but made of particles that don't interact electromagnetically with our matter. Two entire civilizations could exist in the same location without ever knowing about each other, passing through each other like ghosts. Dark matter might be like this parallel universe, sharing our space but remaining forever invisible to us. Despite decades of searching with the most sophisticated detectors ever built, no one has successfully detected dark matter particles directly. Underground laboratories around the world are filled with ultra-sensitive instruments designed to catch dark matter particles as they pass through Earth. But so far, these experiments have come up empty. Either dark matter is even more elusive than we thought, or our understanding of what we're looking for is fundamentally flawed. The mystery deepens when we consider that dark matter isn't just a problem for understanding Andromeda, it appears to be a fundamental component of the entire universe. Every galaxy astronomers have studied shows similar rotation curves, suggesting that dark matter outweighs normal matter everywhere in the cosmos. In galaxy clusters, the largest gravitationally bound structures in the universe, dark matter appears to make up an even higher fraction of the total mass. If dark matter really does dominate the universe, then everything we can see and touch represents just a tiny fraction of cosmic reality. We would be like fish swimming in an ocean, aware only of the water immediately around us, but oblivious to the vast depths that surround us on all sides. The atoms that make up our bodies, our planet, and all the stars we can see would be a minority component in a universe dominated by completely unknown particles. But let's return to what we can observe directly in Andromeda, because even the visible components of the galaxy hold surprises that challenge our understanding of how galaxies form and evolve. The stellar populations of Andromeda tell a complex story of cosmic evolution spanning billions of years. In the galaxy's central bulge, astronomers find predominantly old, red stars. These stellar veterans formed when the universe was much younger and contain relatively few of the heavy elements that are common in younger stars. Their red color comes from their low surface temperatures, a consequence of their advanced age and the way they've evolved over billions of years. These ancient stars are like cosmic archaeologists, preserving information about the conditions that existed when Andromeda was young. By studying their properties, astronomers can reconstruct what the galaxy was like billions of years ago, when star formation rates were much higher and the chemical composition of the interstellar medium was very different from what we observe today. Moving outward from the center, the stellar population gradually changes. The disk regions contain a mix of old and young stars, with the youngest and most massive stars concentrated along the spiral arms. These young stars burn hot and bright, giving the spiral arms their distinctive blue-white glow in color photographs. But it's not just the ages of the stars that vary throughout Andromeda. Their chemical compositions also change in systematic ways that provide clues about how the galaxy formed and evolved. Stars in the central regions tend to be metal-rich in astronomical terms, meaning they contain higher abundances of elements heavier than hydrogen and helium. These heavy elements were forged in the cores of earlier generations of stars and dispersed into space when those stars died in supernova explosions. The fact that central stars are more metal-rich than outer stars suggests that star formation and chemical evolution proceeded differently in different regions of the galaxy. The central regions may have experienced more intense star formation early in Andromeda's history, leading to rapid enrichment in heavy elements. The outer regions, by contrast, may have formed stars more gradually, allowing less time for chemical enrichment. These chemical gradients also provide clues about Andromeda's formation history. Did the galaxy form from the gravitational collapse of a single, massive gas cloud, or did it assemble gradually through the merger of smaller protogalaxies? The chemical patterns observed in Andromeda's stars favor the merger scenario, suggesting that the galaxy we see today is the result of numerous smaller galaxies coming together over billions of years. Evidence for this merger history can be seen throughout Andromeda's structure. Astronomers have identified numerous stellar streams in the galaxy's outer regions, long trails of stars that were likely torn from smaller galaxies as they were absorbed by Andromeda's gravitational field. The most prominent of these, known as the Giant Southern Stream, stretches for over 100,000 light-years and contains the disrupted remnants of what was once an independent dwarf galaxy. These stellar streams are like archaeological artifacts, preserving evidence of Andromeda's violent past. By studying their properties and orbits, astronomers can reconstruct the merger events that created them and build a timeline of Andromeda's growth over cosmic time. But Andromeda's merger history raises troubling questions about the fate of any planetary systems that might have existed in the smaller galaxies it consumed. When galaxies merge, the gravitational disruption can fling stars and their planets into entirely new orbits. Some planetary systems might be ejected from the galaxy entirely, becoming homeless wanderers in the intergalactic void. Others might find themselves in highly elliptical orbits that carry them alternately through the crowded galactic center and the sparse outer halo. For any life that might have evolved on planets in these disrupted systems, galactic mergers would represent catastrophic events on a scale difficult to imagine. Civilizations that had developed over millions or billions of years could find their entire solar system relocated to a completely different galactic environment with new neighbors, new radiation environments, and new gravitational influences. Imagine if our own solar system was suddenly transported from its quiet location in the Milky Way suburbs to the dense, radiation-rich environment near the galactic center. The night sky would be blazing with millions of nearby stars. Deadly cosmic rays would bombard Earth's atmosphere. The gravitational influence of nearby stars might disrupt the orbits of the outer planets. Any civilization that had developed under the original conditions would face challenges that could threaten its very survival. Yet mergers might also create opportunities for life to spread and diversify. As stellar systems are mixed and redistributed throughout the galaxy, they carry with them any organic molecules or even primitive life forms that might exist in comets, asteroids, or planetary atmospheres. In this way, galactic mergers could serve as a mechanism for spreading the building blocks of life across vast regions of space. The scale of Andromeda's past merger activity has surprised astronomers. Initially, they expected that a galaxy as large and massive as Andromeda would have formed relatively recently through the merger of two smaller spirals of comparable size. But observations suggest a more complex history involving the accretion of numerous smaller galaxies over many billions of years. This hierarchical formation model has become the standard paradigm for understanding how large galaxies like Andromeda grew to their current size. According to this picture, the first galaxies to form in the early universe were much smaller than those we see today. Over cosmic time, these small galaxies merged with each other repeatedly, building up the massive structures we observe in the present-day universe. Computer simulations of this process predict that galaxies like Andromeda should be surrounded by numerous small satellite galaxies, the survivors of past merger events that managed to avoid being completely absorbed. And indeed, when astronomers survey the region around Andromeda, they find exactly what the simulations predict: a collection of dwarf galaxies orbiting the larger spiral. The most prominent of these satellites are M32 and M11 small elliptical galaxies that are clearly visible even in modest amateur telescopes. M32 in particular shows signs of having been significantly disrupted by its interactions with Andromeda. Its outer stars have been stripped away, leaving behind a compact core that may represent the remnant of what was once a much larger galaxy. But the satellite system around Andromeda holds surprises that challenge our understanding of galaxy formation. Instead of being randomly distributed around the main galaxy, as computer simulations predict, many of the satellites appear to be arranged in a thin, disk-like structure. This plane of satellites is difficult to explain using standard models of galaxy formation and has led some astronomers to question whether our understanding of dark matter and galaxy evolution is complete. The discovery of this planar structure around Andromeda is particularly intriguing because a similar structure exists around our own Milky Way. The fact that both galaxies show this unexpected organization suggests that there may be fundamental aspects of galaxy formation that we don't yet understand. Some researchers have proposed that the satellite planes could be remnants of ancient filamentary structures that existed when the galaxies first formed. Others suggest they might be the result of specific merger events that aligned the orbital planes of the satellites. Still others argue that the observations might be pointing to modifications in our understanding of gravity or dark matter on galactic scales. These mysteries remind us that despite nearly a century of intensive study, Andromeda continues to surprise us. Every new observation, every improvement in telescope technology, every advance in theoretical understanding reveals new layers of complexity in this cosmic neighbor. Perhaps most humbling of all is the realization that everything we can observe about Andromeda, from its spiral structure to its stellar populations to its satellite galaxies, represents just the tip of an iceberg. The bulk of the galaxy's mass remains invisible and mysterious, composed of dark matter whose nature continues to elude us despite decades of searching. This invisible component isn't just a minor detail in our understanding of Andromeda. It's the dominant constituent of the galaxy, the scaffolding that holds everything else together. Without dark matter, the stars we see would long ago have dispersed into the intergalactic void. The beautiful spiral structure would never have formed. The galaxy as we know it simply wouldn't exist. Yet we know almost nothing about this crucial component of cosmic structure. We don't know what dark matter particles look like, how they interact with each other, or whether they decay over time. We don't know if dark matter has its own complex physics, perhaps even its own periodic table of elements and chemical processes. Here's a thought that should keep you awake at night. If dark matter particles can interact gravitationally, might they be able to form their own complex structures? Could there be dark matter planets, dark matter stars, even dark matter life forms existing parallel to our own visible universe? We might be sharing space with an entire hidden cosmos that we can't directly detect or interact with. The mystery of dark matter in Andromeda is thus much more than an academic puzzle. It represents one of the most fundamental gaps in our understanding of the universe. Solving it could revolutionize physics, unlock new technologies, and reveal entirely new forms of matter and energy that permeate the cosmos. But even as we grapple with these cosmic mysteries, Andromeda continues its inexorable approach toward our own galaxy. Every year it draws roughly 75 million miles closer to the Milky Way. The collision that will eventually merge these two giants is still billions of years away, but it's already influencing how astronomers think about galactic evolution and the ultimate fate of cosmic structure. When Andromeda and the Milky Way finally collide, the resulting merger will mix their stellar populations, redistribute their dark matter halos, and create entirely new structures from the combined material of both galaxies. The invisible components of both galaxies will interact in ways we can barely imagine, possibly revealing new clues about the nature of dark matter itself. Understanding Andromeda's current structure and composition is thus crucial for predicting what will happen during this future collision. The galaxy's dark matter halo, its stellar populations, its gas content, and its magnetic fields will all play roles in determining the outcome of the merger. But that collision is still far in the future. Right now, Andromeda stands as a testament to the complexity and mystery of cosmic structure. It's a galaxy dominated by invisible matter, shaped by violent mergers, and surrounded by satellites arranged in patterns we don't fully understand. Every photon of light we receive from Andromeda carries with it information about processes we're only beginning to comprehend. The galaxy serves as a cosmic laboratory where we can study dark matter, stellar evolution, galactic dynamics, and the hierarchical formation of structure in the universe. As we prepare to delve deeper into Andromeda's secrets, we're reminded that this galaxy is far more than just a beautiful spiral in space. It's a complex, evolving system whose very existence challenges our understanding of matter, gravity, and the fundamental nature of reality itself. Within Andromeda's trillion stars lies a menagerie of cosmic monsters that would make science fiction writers weep with envy. These aren't just ordinary stars like our Sun, peacefully converting hydrogen to helium over billions of years. They're stellar extremes that push the very limits of what's possible under the laws of physics, objects so bizarre and powerful that their existence challenges everything we thought we knew about how stars work. But before we explore these cosmic anomalies, we need to understand what makes Andromeda such a perfect laboratory for studying stellar evolution. The galaxy's enormous size and diverse stellar populations mean it contains examples of virtually every type of star that can exist in the universe. From the smallest red dwarfs, barely massive enough to sustain nuclear fusion, to blue hypergiants that outshine our Sun by millions of times, Andromeda's stellar zoo is unparalleled in its diversity and scope. What makes this even more remarkable is that we can study these objects across an entire galaxy at once, seeing how stellar evolution proceeds under different conditions and environments. In the galaxy's central bulge, where stars are packed thousands of times more densely than in our solar neighborhood, stellar interactions and collisions create phenomena we never see in the Milky Way's more spacious outer regions. Imagine trying to understand human behavior by observing a small rural town. Now imagine you could simultaneously observe a massive metropolitan area with millions of inhabitants living under completely different conditions. That's essentially what Andromeda offers us in terms of stellar populations, a vast cosmic city where we can observe how stars behave under every possible circumstance. In the spiral arms, where massive clouds of gas and dust are constantly being compressed by density waves, we can witness stellar birth on scales that dwarf anything in our local cosmic vicinity. And in the galaxy's extended halo, where ancient stars drift in solitary orbits, we can study stellar populations that formed when the universe was a fraction of its current age. But it's the extreme objects within Andromeda that truly boggle the mind. Consider the hypervelocity stars, stellar speedsters moving so fast they defy every conventional understanding of galactic dynamics. These objects are traveling at speeds of 1,000 kilometers per second or more, fast enough to cross the distance from Earth to the Moon in less than 6 minutes. How does a star achieve such incredible velocities? The most likely explanation involves close encounters with Andromeda's central supermassive black hole, a gravitational monster containing the mass of 140 million suns. When a binary star system ventures too close to this cosmic behemoth, the intense gravitational forces can tear the pair apart. One star gets captured by the black hole, while its companion receives a gravitational slingshot that hurls it across the galaxy at unimaginable speeds. Here's a way to visualize this process. Imagine two ice skaters holding hands and spinning rapidly. If one skater suddenly lets go and grabs onto a fixed post, the other skater will go flying across the rink at tremendous speed. The same principle applies to binary stars near supermassive black holes, except the energies involved are so enormous that the ejected star can reach speeds that would allow it to escape the galaxy entirely. These hypervelocity stars are like cosmic refugees, carrying with them the traumatic story of their encounter with one of the universe's most violent phenomena. Some are moving so fast they'll eventually escape Andromeda entirely, becoming intergalactic wanderers destined to drift alone through the void between galaxies for billions of years. But hypervelocity stars are just the beginning of Andromeda's stellar oddities. Deep within the galaxy's disk lurk luminous blue variables, massive stars caught in a kind of cosmic tantrum. These stellar giants are so unstable they can suddenly brighten by factors of millions before returning to normal, or within time periods ranging from months to years. The most famous example in our own galaxy is Eta Carinae, a star that underwent a massive eruption in the 1840s, briefly becoming one of the brightest stars in the sky before fading back to relative obscurity. But Andromeda contains dozens of these cosmic time bombs, each one representing a star on the very edge of stability. Luminous blue variables exist in a precarious balance between the inward pull of their own gravity and the outward pressure of the radiation they produce. They're so massive, sometimes exceeding 150 times the mass of our Sun, that their radiation pressure nearly overcomes their gravitational self-attraction. The slightest perturbation can tip them over the edge, causing them to violently expel their outer layers in eruptions that can be seen across intergalactic distances. When these monsters finally exhaust their nuclear fuel, they don't go quietly. They explode as hypernovae, stellar detonations so powerful they can outshine entire galaxies for weeks or months. These explosions don't just create spectacular light shows, they forge the heaviest elements in the universe through nuclear processes so violent they can only occur in the final seconds of a massive star's life. Here's something that connects you personally to these cosmic explosions: the gold in your jewelry, the platinum in catalytic converters, the uranium used in nuclear reactors. All of these elements were created in the cores of exploding stars like Andromeda's luminous blue variables. Every heavy element in your body, from the calcium in your bones to the iron in your blood, was forged in stellar furnaces and scattered across space by supernova explosions. But even hypernovae pale in comparison to some of the exotic objects that Andromeda harbors in its depths. Consider the magnetars, neutron stars with magnetic fields so intense they warp the very structure of matter itself. These objects are the collapsed cores of massive stars, compressed to densities so extreme that a teaspoon of neutron star material would weigh as much as Mount Everest. A typical neutron star is only about 20 kilometers across, roughly the size of Manhattan, yet it contains more mass than our entire Sun. The gravitational field at its surface is so strong that if you could somehow stand on a neutron star, you would weigh about 100 billion times more than you do on Earth. The escape velocity from a neutron star's surface is roughly 1/3 the speed of light. But magnetars take this cosmic extremism to even greater heights. Their magnetic fields are trillions of times stronger than Earth's, so powerful that they can strip electrons from atoms at distances of thousands of kilometers. If a magnetar existed at the distance of the Moon from Earth, its magnetic field would erase every credit card, hard drive, and electronic device on the planet. The energy stored in a magnetar's magnetic field is almost beyond comprehension. In a single magnetic field reconfiguration event, a magnetar can release more energy in 1/10 of a second than our Sun produces in 100,000 years. These starquakes, as they're called, twist and crack the neutron star's crust, releasing bursts of gamma rays so intense they can affect Earth's atmosphere from distances of thousands of light years. Andromeda likely harbors dozens of these magnetic monsters, though detecting them across intergalactic distances pushes our instruments to their absolute limits. Each one represents an experiment in physics under conditions so extreme they can't be replicated anywhere on Earth or in any laboratory we can imagine building. But perhaps the most intriguing stellar objects in Andromeda are the carbon stars, ancient red giants that have begun manufacturing their own carbon through nuclear fusion processes. As these stars age and cool, they develop complex atmospheric chemistry that creates conditions unlike anywhere else in the universe. The surfaces of carbon stars are factories for organic molecules, producing complex carbon compounds that serve as the building blocks for more sophisticated chemistry. When these stars shed their outer layers through powerful stellar winds, they scatter these organic precursors throughout the galaxy, seeding interstellar space with the raw materials that could eventually lead to life. Some carbon stars in Andromeda are surrounded by vast shells of carbon-rich material stretching for light years in every direction. These shells contain not just simple carbon compounds but complex organic molecules including polycyclic aromatic hydrocarbons, the same class of molecules found in soot and coal on Earth. The implications are profound. Every carbon atom in your DNA may have been manufactured in the core of a dying star, possibly in a galaxy like Andromeda. The organic chemistry that makes life possible appears to be a natural consequence of stellar evolution, suggesting that the building blocks of biology are being manufactured throughout the universe. But Andromeda's stellar population includes objects even more exotic than carbon stars and magnetars. Hidden within the galaxy's vast expanse are likely numerous stellar mass black holes, the collapsed remnants of the most massive stars. Unlike neutron stars, which at least have a surface you could theoretically touch, black holes have crossed the ultimate threshold. They become regions of space-time so warped that not even light can escape their gravitational pull. Most stellar mass black holes are invisible, detectable only through their gravitational effects on nearby matter. But some exist in binary systems, slowly stripping material from companion stars. As this stolen matter spirals into the black hole, it heats up to temperatures of millions of degrees, glowing with X-ray radiation that can be detected across vast distances. These X-ray binaries are among the most violent environments in the universe. The material falling into the black hole doesn't simply disappear, it forms an accretion disk that becomes a particle accelerator of cosmic proportions. Charged particles are accelerated to nearly the speed of light, producing high-energy radiation and sometimes launching jets of material that extend for thousands of light years. Andromeda likely contains thousands of stellar mass black holes, most of them lurking invisibly in the galactic disk. Occasionally, one might wander close enough to our line of sight to gravitationally lens the light from a more distant star, causing it to briefly brighten in a characteristic pattern. These microlensing events offer one of the few ways to detect isolated black holes across intergalactic distances. But stellar mass black holes aren't the most extreme gravitational objects in Andromeda. At the galaxy's very heart lurks something far more massive and mysterious, a supermassive black hole containing roughly 140 million times the mass of our Sun. This central monster, designated M31, is one of the most massive black holes in our local cosmic neighborhood. The event horizon of M31, the boundary beyond which nothing can escape, has a diameter of roughly 840 million kilometers, large enough to encompass the orbit of Jupiter with room to spare. The gravitational forces near this boundary are so intense that space and time themselves become severely distorted. An astronaut falling toward M31 would experience tidal forces so strong they would stretch her body like taffy long before she crossed the event horizon. But here's what's truly mysterious about Andromeda's central black hole. It's remarkably quiet. Unlike some supermassive black holes, which actively consume large amounts of material and shine brighter than entire galaxies, M31 appears to be in a dormant state. It's not currently feeding on significant amounts of matter, making it difficult to study despite its enormous mass. This dormancy might be temporary. Supermassive black holes can remain quiet for millions of years before suddenly roaring back to life when new material falls within their grasp. If M31 were to begin actively feeding again, it could transform Andromeda's central regions, sterilizing vast volumes of space with its radiation and fundamentally altering the galaxy's structure and evolution. The region immediately around M31 is one of the most extreme environments in the local universe. Stars in the innermost regions orbit the black hole at speeds of thousands of kilometers per second, completing orbits that would take light itself several minutes to traverse. The gravitational field is so strong that these stars experience significant time dilation. Time literally runs slower for them than it does for stars in Andromeda's outer regions. These inner stars exist in a cosmic shooting gallery where gravitational interactions can fling objects around at incredible velocities. Some stars get accelerated to such high speeds that they're ejected from the galactic center entirely, becoming the hypervelocity stars we discussed earlier. Others are torn apart by tidal forces, their material joining the thin accretion flow that slowly feeds the black hole. But even in this violent environment, star formation continues. The extreme conditions near the galactic center can compress gas clouds to densities that trigger the birth of new stars, though these stellar infants face a harsh existence in the black hole's neighborhood. Many will be disrupted by gravitational interactions before they can settle into stable orbits. The study of Andromeda's central black hole provides crucial insights into how these cosmic monsters influence galactic evolution. There appears to be a fundamental relationship between the mass of a galaxy's central black hole and the properties of the galaxy's stellar bulge. Galaxies with more massive central black holes tend to have larger, more massive bulges, suggesting that the growth of supermassive black holes and their host galaxies are intimately connected. This connection might explain some of the puzzling features of galaxy formation and evolution. As supermassive black holes grow by consuming material, they release enormous amounts of energy that can heat and disperse the gas throughout their host galaxies. This feedback process might regulate star formation, preventing galaxies from growing too large or forming stars too rapidly. But Andromeda's stellar extremes aren't limited to single stars and black holes. The galaxy also contains some of the most massive and luminous star clusters in the local universe. These globular clusters are dense collections of hundreds of thousands or even millions of stars, all bound together by their mutual gravitational attraction. Andromeda has over 500 known globular clusters, more than twice the number found in the Milky Way. Some of these clusters are among the most massive stellar systems known, containing the equivalent of several million suns worth of material packed into spherical regions, only a few dozen light-years across. The stars in these clusters are packed so densely that collisions between them are relatively common on astronomical timescales. When two stars collide and merge, they can create objects with properties unlike anything formed through normal stellar evolution. These collision products, known as blue stragglers, appear younger and more massive than they should based on the cluster's age. Some globular clusters in Andromeda may harbor intermediate mass black holes at their centers, objects with masses between stellar mass black holes and supermassive black holes. These intermediate mass black holes are among the most elusive objects in astronomy, predicted by theory but difficult to observe directly. If they exist in Andromeda's globular clusters, they would provide crucial insights into how supermassive black holes might have formed in the early universe. The globular cluster system around Andromeda also preserves evidence of the galaxy's merger history. Some clusters have unusual chemical compositions that suggest they formed in smaller galaxies before being incorporated into Andromeda through galactic mergers. Others follow orbital patterns that seem inconsistent with formation within Andromeda itself. By studying the ages, chemical compositions, and orbital properties of Andromeda's globular clusters, astronomers can reconstruct the galaxy's assembly history over billions of years. Each cluster is like a fossil record, preserving information about the conditions that existed when it formed. But perhaps the most remarkable aspect of Andromeda's stellar population is its sheer diversity. The galaxy contains examples of virtually every type of stellar object predicted by theory, from the most common red dwarfs to the rarest and most exotic hypergiants. This diversity arises from the galaxy's complex formation history and its varied environments. In the dense central bulge, stellar interactions and mergers create populations of unusual stars with properties that depend on their collision histories. In the spiral arms, ongoing star formation produces young, massive stars that will live fast and die young in spectacular explosions. In the outer halo, ancient stars preserve the chemical signatures of the early universe, providing windows into cosmic conditions billions of years ago. The magnetic fields threading Andromeda's disk also play crucial roles in stellar evolution. These fields can influence how gas collapses to form new stars, affect the mass loss rates of evolved stars, and even determine the properties of stellar explosions. The interplay between stellar evolution and magnetic fields is one of the most active areas of research in modern astrophysics. Recent observations have revealed that Andromeda's magnetic field is much more complex and dynamic than initially expected. Rather than a simple dipole field like Earth's, the galaxy's magnetic field shows intricate structures that vary throughout the disk. These variations are likely driven by the complex motions of charged particles in the galaxy's plasma, influenced by stellar winds, supernova explosions, and the rotation of the galaxy itself. The stellar winds from massive stars in Andromeda's spiral arms create vast bubbles of hot, ionized gas that can extend for hundreds of light years. These superbubbles are powered by the combined effects of stellar winds and supernova explosions from associations of massive stars. They play crucial roles in mixing heavy elements throughout the galaxy and regulating the rate of star formation. When multiple superbubbles interact and merge, they can create even larger structures called supershells, cavities in the interstellar medium that can span thousands of light years. These structures channel the flow of gas throughout the galaxy, creating pathways for material to move from the star-forming disk to the extended halo. The stellar content of Andromeda also includes populations of variable stars that serve as cosmic lighthouses, their regular pulsations providing precise tools for measuring distances and studying stellar physics. Cepheid variables, the same stars Hubble used to determine Andromeda's distance, are just one type among many. RR Lyrae variables, found primarily in the galaxy's halo and globular clusters, pulsate with periods measured in hours rather than days. These stars are less massive than Cepheids, but follow their own period-luminosity relationship, making them useful for studying the galaxy's oldest stellar populations. Long-period variables, including mirror-type stars, can vary in brightness by factors of hundreds over periods of months or years. These are typically evolved stars that have begun to pulsate as they exhaust their nuclear fuel, shedding mass through powerful stellar winds that enrich the interstellar medium with heavy elements. The study of variable stars in Andromeda has revealed that stellar pulsation is far more complex than initially thought. Many variables show multiple periods simultaneously, indicating that different layers within the star are pulsating at different rates. Some show irregular variations superimposed on their regular pulsations, suggesting that stellar atmospheres are highly dynamic and turbulent environments. But perhaps the most intriguing stellar objects in Andromeda are those that challenge our basic understanding of stellar physics. These include stars that appear to be older than the universe itself, based on standard stellar evolution models. Others seem to have chemical compositions that shouldn't be possible, given their apparent ages and formation environments. These stellar anomalies force astronomers to reconsider fundamental assumptions about how stars form and evolve. They might indicate that stellar physics under extreme conditions is more complex than current models predict, or they could point to exotic physical processes that haven't been included in standard theories. Some of these anomalous stars might be the products of stellar mergers, events that can rejuvenate old stars and give them properties that seem inconsistent with their true ages. Others might have formed under unusual conditions in the early universe, when the chemical composition of the galaxy was very different from what we observe today. The existence of these stellar puzzles in Andromeda reminds us that despite decades of progress in understanding stellar evolution, many mysteries remain. Each new generation of telescopes and instruments reveals new complexities and challenges to our theoretical models. As we continue to study Andromeda's stellar populations with ever-improving technology, we're likely to discover even more exotic objects that push the boundaries of stellar physics. The galaxy serves as a vast laboratory where nature conducts experiments under conditions we can barely imagine, creating phenomena that test the limits of our understanding. From hypervelocity stars racing through space at incredible speeds to magnetars with magnetic fields that could strip atoms apart. From carbon stars manufacturing the building blocks of life to black holes that warp space and time itself, Andromeda's stellar menagerie represents the full spectrum of cosmic extremes. But these stellar objects don't exist in isolation. They're part of a complex, interconnected system where the death of one star can trigger the birth of another, where stellar winds and magnetic fields shake the flow of gas throughout the galaxy, and where the most extreme objects influence the evolution of entire stellar populations. Understanding these connections and feedback processes is crucial for comprehending how galaxies like Andromeda evolve over cosmic time. The stellar extremes we observe today are both products of the galaxy's past evolution and drivers of its future development, creating a cosmic cycle that has been operating for billions of years and will continue for billions more. With 1 trillion stars scattered across Andromeda's vast expanse, the mathematical probability that we're looking at a galaxy completely devoid of life borders on the impossible. But here's the crushing reality: detecting life in another galaxy, even one as relatively close as Andromeda, represents perhaps the greatest observational challenge in all of science. We're essentially trying to find evidence of biology across a distance so vast that the light carrying that evidence has been traveling toward us since before our species existed. Yet the search continues, driven by a question that haunts every astronomer who has ever pointed a telescope at Andromeda's spiral arms. If life arose in our galaxy, with its particular history and chemical evolution, what might have emerged in a galaxy that's larger, older, and has experienced a far more violent merger history? The answer could reshape our understanding of life's place in the cosmic order. To appreciate the scale of this challenge, consider what we're trying to accomplish. In our own galaxy, we've confirmed the existence of over 5,000 exoplanets, worlds orbiting stars other than our Sun. But these discoveries required decades of technological development and observation of stars that are, at most, a few thousand light-years away. Andromeda's nearest stars are 2.5 million light-years distant, making them roughly 1,000 times farther than the most distant exoplanets we can currently study in detail. The mathematical problem is brutal. The light from even Andromeda's brightest stars is already stretched to the limits of our most powerful telescopes. A planet orbiting one of these stars would be billions of times fainter still, lost in the overwhelming glare of its host star. It would be like trying to spot a firefly hovering next to a searchlight from a distance of several thousand miles. But astronomers are nothing if not resourceful, and the techniques being developed to search for planets in Andromeda push the boundaries of what's technologically possible. The most promising approach involves gravitational microlensing, a phenomenon predicted by Einstein's theory of general relativity that turns massive objects into natural telescopes. When a star passes directly between us and a more distant background star, its gravity bends and focuses the background star's light, causing it to appear brighter for a period of days or weeks. If the foreground star has planets, these worlds can create additional brightening events, brief spikes in the light curve that reveal their presence even though the planets themselves remain completely invisible. Here's what makes microlensing so powerful. It doesn't depend on the planet's brightness or its proximity to its host star. A planet's gravitational field can create a detectable signal, regardless of whether it's a hot Jupiter hugging close to its star or a frozen world in the outer reaches of its solar system. For the first time, we have a technique that could potentially detect Earth-sized worlds around stars in other galaxies. But the challenges are immense. Microlensing events are rare and unpredictable. To have any hope of detecting planetary signals, astronomers need to monitor millions of stars simultaneously, watching for the telltale brightening that indicates a lensing event is in progress. Then they need to catch the much briefer and subtler planetary signatures that might last only hours within the longer stellar event. Several teams of astronomers are already attempting this ambitious survey. The optical gravitational lensing experiment, based in Chile, monitors dense stellar fields in Andromeda night after night, building up a database of millions of stellar light curves. Advanced computer algorithms sift through this data, searching for the characteristic patterns that would indicate planetary companions. The first tentative detection of an extragalactic planet was announced in 2020, though not in Andromeda itself, but in the more distant Whirlpool Galaxy. The signal was detected through X-ray emissions rather than optical light, as a planet-sized object appeared to transit in front of an X-ray binary system. While this detection remains controversial and unconfirmed, it demonstrates that finding planets in other galaxies is at least theoretically possible. For Andromeda, the numbers are encouraging. With roughly 1 trillion stars, and assuming that planets are as common around Andromeda's stars as they appear to be around stars in the Milky Way, the galaxy could harbour anywhere from 1 to 10 trillion worlds. Even if only a tiny fraction of these planets are capable of supporting life as we know it, we could still be looking at billions of potentially habitable worlds. But habitability in Andromeda might look very different from habitability in our own galaxy. Andromeda's more violent merger history means that many of its stellar systems have been disrupted and relocated multiple times over the galaxy's lifetime. A planet that formed in the galaxy's outer regions might now find itself in the crowded central bulge, subjected to intense radiation from nearby stars and frequent gravitational perturbations from stellar encounters. Conversely, worlds that originally formed in the hostile central regions might have been flung outward by gravitational slingshot effects, finding themselves in the quieter galactic suburbs where conditions are more conducive to stable, long-term evolution. This mixing and redistribution of planetary systems could have created opportunities for life to adapt to a much wider range of galactic environments than we see in our own, more sedate galaxy. The chemical evolution of Andromeda also presents intriguing possibilities for astrobiology. The galaxy's early merger history likely triggered intense episodes of star formation, rapidly enriching the interstellar medium with heavy elements necessary for planet formation and potentially life. This means that potentially habitable worlds might have formed earlier in Andromeda's history than in the Milky Way, giving life additional billions of years to evolve and develop. But here's a thought experiment that illustrates the profound challenges of searching for life across intergalactic distances. Imagine trying to detect a campfire from orbit around Mars. The fire itself would be completely invisible, but you might be able to detect subtle changes in the atmospheric composition of the entire planet if the smoke was somehow spread globally. This is essentially what we're trying to do with Andromeda, detect planetary-scale biosignatures from a distance of 2.5 million light-years. On the other hand, the same violent processes that accelerated chemical evolution might have created environments hostile to the development of complex life. The high supernova rates associated with starburst episodes would have flooded large regions of the galaxy with harmful radiation. The gravitational disruptions from galactic mergers could have destabilized planetary orbits, sending worlds careening into their host stars or ejecting them into the frozen darkness of interstellar space. These competing factors make Andromeda a fascinating natural laboratory for testing our understanding of astrobiology on galactic scales. If life is robust and adaptable, capable of surviving and thriving under a wide range of conditions, then Andromeda might be teeming with biological activity. If life is fragile and requires very specific conditions to develop and persist, then the galaxy's turbulent history might have severely limited the opportunities for complex organisms to evolve. But detecting life, even if it exists in abundance throughout Andromeda, presents challenges that go far beyond simply finding planets. Life detection requires identifying biosignatures, chemical or physical indicators that living processes are at work. In our own solar system, we can send spacecraft to directly sample the atmospheres and surfaces of other worlds. For exoplanets in the Milky Way, we can sometimes analyze starlight that has passed through their atmospheres, looking for the spectral signatures of molecules like oxygen, water vapor, and methane that might indicate biological activity. For worlds in Andromeda, such direct atmospheric analysis is currently impossible. The combined light from an entire star and any planets that might orbit it appears as a single point source in even our most powerful telescopes. Separating the faint reflected light of a planet from the overwhelming brightness of its host star across intergalactic distances would require telescopes hundreds of times larger than anything currently planned. This limitation forces us to think creatively about alternative approaches to life detection in other galaxies. One possibility involves looking for biosignatures on a planetary scale rather than trying to analyze individual worlds. If life is abundant throughout Andromeda, it might have modified the galaxy's overall spectral signature in detectable ways. For example, if photosynthetic organisms are common throughout the galaxy, they might have altered the atmospheric compositions of billions of worlds, creating a subtle but detectable change in the combined light spectrum of entire stellar populations. Advanced civilizations might have modified their environments so extensively that their technological signatures are visible on galactic scales, perhaps through the construction of megastructures that alter the energy output of significant fractions of the galaxy's stars. The search for such technosignatures represents one of the most speculative but potentially rewarding approaches to detecting life in Andromeda. If the galaxy harbors civilizations significantly more advanced than our own, they might have developed technologies that leave unmistakable imprints on their cosmic environment. The most commonly discussed megastructure is the Dyson sphere, a hypothetical construct that completely surrounds a star to capture all of its energy output. A civilization that built Dyson spheres around significant numbers of stars would alter the galaxy's infrared signature in ways that might be detectable from Earth. The stars would appear dimmer in visible light, but brighter in the infrared as the spheres absorb stellar radiation and re-emit it as heat. Several teams of astronomers have searched for such signatures in Andromeda and other nearby galaxies, looking for stars that appear anomalously bright in infrared wavelengths. So far, no convincing examples have been found, but the searches are limited by the sensitivity of current infrared telescopes and our understanding of what alien megastructures might actually look like. Here's a mind-bending possibility. What if advanced civilizations in Andromeda have moved beyond individual megastructures to manipulating the galaxy itself? They might have rearranged entire star systems, created artificial nebulae, or even modified the galaxy's spiral structure for purposes we can't imagine. From our perspective, these modifications might appear to be natural features, but they could actually be the products of engineering on scales that dwarf anything in human experience. Other potential technosignatures might include the artificial modification of stellar evolution, perhaps through stellar engineering projects that alter how stars burn their nuclear fuel. An advanced civilization might extend the lifetimes of stars by removing excess mass or adding fresh hydrogen fuel, creating stellar populations with properties that differ from natural stellar evolution models. More speculatively, truly advanced civilizations might have developed technologies that allow them to manipulate matter and energy on galactic scales. They might create artificial black holes for energy generation, build wormholes for faster than light travel, or even modify the large-scale structure of their galaxy to suit their needs. While such possibilities sound like science fiction, they represent logical extensions of technologies that might develop over the millions or billions of years that advanced civilizations could potentially exist. The Drake equation, originally formulated to estimate the number of communicating civilizations in our own galaxy, becomes even more speculative when applied to Andromeda. We must estimate not only the rate of star formation and the fraction of stars that have planets, but also how Andromeda's unique history might have affected the development of life and intelligence. Consider just the question of stellar lifetimes. Andromeda's early starburst episodes would have created generations of massive, short-lived stars that flooded the galaxy with heavy elements, but also with harmful radiation. The peak epochs of star formation might have been hostile to life development, but the quieter periods that followed could have provided ideal conditions for biological evolution. The galaxy's merger history adds another layer of complexity. Each major merger event would have disrupted countless planetary systems, but it would also have mixed stellar populations and potentially spread life-bearing material throughout the galaxy. If life first developed in one region of Andromeda, subsequent mergers might have distributed it to environments where it could diversify and evolve in new directions. The time factor is perhaps most intriguing. If life developed earlier in Andromeda's history than in the Milky Way, then any civilizations that arose there would have had additional billions of years to advance beyond anything we can currently imagine. The gap between their technological capabilities and our own might be so vast that we wouldn't recognize their activities as artificial even if we were looking directly at them. This possibility raises profound questions about the nature of intelligence and consciousness on cosmic timescales. What does a civilization look like after millions of years of continuous development? Do they remain recognizably biological, or do they transcend physical existence entirely? Might they have evolved into forms of consciousness that exist as patterns of information in the quantum vacuum itself? Such speculations quickly enter the realm of science fiction, but they're grounded in serious scientific questions about the ultimate limits of intelligence and technology. If consciousness is indeed information processing, as many cognitive scientists believe, then sufficiently advanced civilizations might eventually exist as pure information, liberated from the constraints of matter and energy that limit biological beings. From our perspective, such post-biological intelligences might be completely invisible, their activities operating on scales of space, time, and complexity that we can't comprehend. They might be carrying out projects that span millions of years and encompass entire galactic clusters, but appear to us as natural processes because we lack the conceptual framework to recognize them as artificial. This possibility, sometimes called the transcension hypothesis, suggests that truly advanced civilizations might turn inward rather than outward, focusing on the exploration of inner space rather than outer space. Instead of building visible megastructures or expanding across the galaxy, they might retreat into increasingly sophisticated virtual realities or explore the computational possibilities of manipulating matter and energy on quantum scales. If this hypothesis is correct, then the absence of obvious alien artifacts in Andromeda might not indicate an absence of intelligence. Instead, it might suggest that any civilizations that developed there have evolved beyond the need for crude physical constructions, pursuing goals and activities that are literally inconceivable to beings at our current level of development. But even if advanced civilizations in Andromeda have transcended physical existence, there might still be traces of their earlier phases of development. Archaeological remnants of their technological civilizations might persist long after the beings themselves have evolved beyond material existence. Ruined megastructures, abandoned colonies, or even fossilized remnants of extinct species might provide evidence of past intelligence. The challenge is distinguishing such artifacts from natural phenomena across intergalactic distances. A Dyson sphere that has partially collapsed might look like a naturally variable star. The ruins of a vast space-based civilization might appear as an unusually clumpy distribution of debris around certain stellar systems. Even direct artifacts like radio transmissions or laser communications might be indistinguishable from natural astrophysical processes when observed from millions of light-years away. Moreover, any signals we might detect from Andromeda would be ancient history by the time they reach us. The light we see from the galaxy today left its stars 2.5 million years ago, when our own ancestors were just learning to use stone tools. If civilizations in Andromeda are broadcasting radio signals or laser communications, we're seeing their activities as they existed during what would be their equivalent of our Stone Age. This temporal disconnect adds another layer of complexity to the search for extraterrestrial intelligence in other galaxies. We're not looking for evidence of alien civilizations as they exist today, but as they existed millions of years ago. They might have developed far beyond whatever signals they were transmitting when the light we're now receiving first began its journey across intergalactic space. Despite these challenges, several research groups continue to search for artificial signals from Andromeda and other nearby galaxies. The SETI Institute regularly surveys the galaxy across multiple wavelengths, looking for narrow-band radio signals or other signatures that might indicate technological activity. Advanced signal processing techniques can sometimes distinguish artificial signals from natural radio emissions, even across vast distances. The search for optical SETT signals focuses on looking for brief, intense laser flashes that might represent attempts at interstellar communication. A sufficiently powerful laser pulse could outshine its host star for brief periods, creating detectable signals even across intergalactic distances. While no confirmed artificial signals have been detected from Andromeda, the searches continue to improve in sensitivity and sophistication. But perhaps the most intriguing possibility is that we're already seeing evidence of life and intelligence in Andromeda, but we don't recognize it as such. The galaxy's complex structure, with its disturbed spiral arms, unusual stellar streams, and puzzling satellite configurations, might not be entirely natural. Some of these features could be the result of large-scale engineering projects carried out by civilizations whose capabilities dwarf our own. The planar arrangement of Andromeda's satellite galaxies, for instance, is difficult to explain using standard models of galaxy formation. While natural processes might account for this structure, it's also possible that it represents the result of intentional manipulation by beings capable of moving entire galaxies into desired configurations. Here's a thought experiment that illustrates this possibility. Imagine an ant trying to understand why the flowers in a garden are arranged in neat rows. The ant might develop elaborate theories about natural processes that could create such regular patterns, never realizing that the arrangement is actually the result of intelligent design by beings whose existence it can't even conceive of. Similarly, some of the galaxy's stellar streams and tidal features might not be entirely the result of natural gravitational interactions. An advanced civilization might have deliberately disrupted smaller galaxies to create specific patterns in the stellar distribution, perhaps as a form of galactic-scale art or communication that we're only now beginning to recognize. These possibilities highlight the fundamental challenge of searching for life and intelligence in Andromeda. We're looking for phenomena that might be completely outside our current conceptual frameworks. Life in other galaxies might have evolved in directions that we can't imagine, developing capabilities and pursuing goals that are literally inconceivable from our current perspective. The chemical differences between Andromeda and the Milky Way also open up possibilities for entirely different biochemistries. While life on Earth is based on carbon chemistry and liquid water, life in Andromeda might have evolved alternative solutions to the challenges of metabolism, reproduction, and information storage. Silicon-based life, ammonia-based biochemistry, or even more exotic possibilities involving plasma physics or quantum processes might have emerged under the different conditions present in Andromeda's stellar populations. The galaxy's higher metallicity in certain regions might have enabled the formation of complex molecules and structures that couldn't exist in the metal-poor environment of the early Milky Way. Conversely, regions that were stripped of heavy elements during merger events might have produced life forms adapted to extremely simple chemical environments, perhaps developing biochemistries that are more efficient than our own carbon-based systems. The diversity of stellar environments in Andromeda also creates opportunities for life to develop around types of stars that are uncommon in our local galactic neighborhood. The galaxy contains numerous examples of stellar populations that formed under different conditions than those that produced our Sun, potentially creating planetary systems with properties unlike anything in the Milky Way. Red dwarf stars, which make up the vast majority of stellar populations in both galaxies, present particularly intriguing possibilities for astrobiology. These small, long-lived stars can continue burning for trillions of years, providing stable energy sources for planetary systems long after more massive stars have died. Any life that develops around red dwarfs would have enormous spans of time available for evolution and development. However, red dwarf planets face unique challenges, including tidal locking, stellar flares, and radiation environments very different from those around Sun-like stars. Life that evolved in such environments might look nothing like terrestrial biology, perhaps developing ways to harness stellar radiation directly or existing in forms that can withstand intense electromagnetic fields and particle bombardment. The massive star-forming regions in Andromeda's spiral arms also create environments where life might develop under conditions of intense radiation and rapid stellar evolution. While such environments might seem hostile to life, they also provide abundant energy and complex chemistry that could drive alternative forms of evolution. Some theoretical biologists have speculated about radiation-based life forms that might evolve in such environments, organisms that use high-energy photons directly for metabolism rather than relying on chemical bonds. While purely speculative, such life forms might thrive in the intense radiation fields around massive stars, developing capabilities that would be impossible in the gentler environments around stars like our Sun. As we continue to develop more powerful telescopes and more sophisticated analysis techniques, our ability to search for life in Andromeda will undoubtedly improve. The next generation of space-based telescopes might be able to detect the combined biosignatures of billions of worlds, revealing whether life is a common or rare phenomenon on galactic scales. Advanced interferometry techniques might eventually allow us to directly image some of the largest planets around Andromeda's nearest and brightest stars, providing our first glimpses of worlds in another galaxy. Even if we can't detect life directly, we might be able to study the atmospheric compositions and surface conditions of these distant worlds, learning about the diversity of planetary environments that exist beyond our own galaxy. The search for life in Andromeda thus represents both an observational challenge and a conceptual frontier. It forces us to think about biology, intelligence, and technology on scales vastly larger than anything in human experience. It challenges us to imagine forms of life and consciousness that might be completely alien to our earthbound perspective. Whether we find evidence of life in Andromeda or not, the search itself transforms our understanding of our place in the cosmic order. It reminds us that our galaxy is just one among billions, each potentially harboring its own forms of complexity, consciousness, and creativity. As Andromeda continues its approach toward an eventual collision with the Milky Way, these questions become more than academic. If both galaxies harbor life, then their merger will represent not just a gravitational interaction, but a biological one, potentially bringing together two independent experiments in evolution that have been proceeding along separate paths for billions of years. The collision might destroy existing biospheres, but it might also create new opportunities for life to develop and spread. The gravitational chaos will mix stellar populations, redistribute planetary systems, and create new stellar formation regions where life might emerge in forms we've never imagined. But that collision is still billions of years in the future. Right now, Andromeda stands as a cosmic question mark, challenging us to expand our understanding of what's possible in the universe and our conception of humanity's place within the vast community of intelligence that might exist among the stars. Every year, without fail, Andromeda draws 75 million miles closer to our galaxy. That might not sound like much on cosmic scales, but it represents one of the most significant events that will ever occur in our local region of the universe. We are witnessing the final stages of a gravitational dance that began billions of years ago, and its climax will reshape everything we know about our cosmic neighborhood. But here's what makes this collision truly extraordinary. We can predict exactly what will happen. Using the most sophisticated computer simulations ever created, astronomers have mapped out the entire sequence of events that will unfold over the next 10 billion years. It's a cosmic choreography of destruction and creation that will play out on scales so vast they challenge human comprehension. The story begins with a simple measurement that revealed one of the most shocking discoveries in modern astronomy. In the 1990s, astronomers using the Hubble Space Telescope began making precise measurements of Andromeda's motion across the sky. What they found defied everything they expected to see in an expanding universe. While most galaxies are moving away from us due to cosmic expansion, Andromeda is racing toward us at 250,000 miles per hour. That's fast enough to travel from Earth to the Moon in just 1 hour. More importantly, when astronomers traced the galaxy's trajectory into the future, they made a stunning realization. Andromeda is on a direct collision course with the Milky Way. Here's a way to put that speed in perspective. If you could somehow travel at Andromeda's approach velocity, you could circle the Earth at the equator in just 6 minutes. You could fly from New York to Los Angeles in about 30 seconds. The International Space Station, which orbits Earth at 17,500 mph, would seem to be crawling in comparison. The discovery sent shockwaves through the astronomical community. Galaxy collisions had been observed in distant parts of the universe, but they were always remote events happening to other galaxies billions of light years away. The idea that our own galaxy was destined for such a fate was almost too enormous to comprehend. Initial calculations suggested the collision would occur in about 3 billion years, but more recent and precise measurements using the Gaia Space Observatory have refined this estimate. The first close encounter between the two galaxies will occur in approximately 4.5 billion years, with the final merger taking place roughly 2 billion years after that. To put this timeline in perspective, when the collision begins, our Sun will be approaching the end of its main sequence lifetime, having swelled into a red giant that may well have already rendered Earth uninhabitable. By the time the merger is complete, our solar system's fate will have been determined by forces far more powerful than stellar evolution. But what exactly happens when two massive galaxies collide? The process is nothing like the violent crashes we might imagine. Galaxies are mostly empty space, and the probability of any two stars actually colliding during the merger is vanishingly small. Instead, what we're witnessing is a gravitational interaction on the largest possible scale, a slow-motion ballet that will unfold over billions of years. Here's an analogy that captures the scale and nature of this collision. Imagine two swarms of gnats, each containing trillions of individual insects, flying toward each other. When the swarms interpenetrate, very few individual gnats will actually collide with each other. They'll mostly pass through the spaces between the insects in the other swarm. But the gravitational interaction between the swarms will dramatically alter their overall structure and motion. The first signs of the approaching collision are already beginning to manifest, though they're subtle enough that most people don't realize we're already in the early stages of this cosmic event. Andromeda's gravitational influence is starting to affect the motion of our galaxy's outer stars and satellite galaxies. The Milky Way's disk is beginning to show slight warps and distortions that may be caused by Andromeda's tidal forces. As the galaxies draw closer, these effects will become more pronounced. Computer simulations show that the first dramatic changes will occur when the galaxies are still about 650,000 light-years apart, roughly 3 times their current separation. At this distance, the gravitational forces between the two galaxies will begin to strip away their outer layers of stars, creating vast tidal streams that stretch across millions of light-years. These tidal interactions will be spectacular to witness if any observers still exist to see them. Long streamers of stars will be pulled from both galaxies, creating bridge-like structures that connect the two cosmic giants. Some stars will be accelerated to such high velocities that they'll be flung completely out of the system, becoming intergalactic wanderers destined to drift alone in the void between galaxy clusters. Think about what this means for any civilizations that might exist during this phase of the collision. The night sky would be a constantly changing tapestry, with new stars appearing and disappearing as stellar streams form and dissolve. Navigation by the stars would become impossible as familiar constellations are torn apart and scattered. The very concept of a stable galactic home would lose all meaning. The disruption will be asymmetric, reflecting the fact that Andromeda is significantly more massive than the Milky Way. Our galaxy will lose a larger fraction of its stars to tidal stripping, while Andromeda will remain more intact during the early stages of the interaction. This mass difference means that when astronomers speak of the Andromeda-Milky Way collision, they're really describing the consumption of our galaxy by its larger neighbor. But the most dramatic effects will occur at the galaxy's centers, where their supermassive black holes will begin one of the most violent gravitational interactions possible in the universe. As the two black holes approach each other, they'll create a binary system that generates gravitational waves powerful enough to ripple the fabric of space-time itself. The Milky Way's central black hole, Sagittarius A, contains roughly 4 million solar masses. Andromeda's central black hole, M31, is much more massive at 140 million solar masses. When these two gravitational monsters begin orbiting each other, they'll create a cosmic maelstrom that will completely reshape the central regions of both galaxies. Stars in the vicinity of the black hole binary will be subjected to gravitational forces that change rapidly and unpredictably. Some will be accelerated to incredible velocities and ejected from the system entirely. These hypervelocity stars will carry with them the story of their traumatic encounter with one of the most extreme gravitational environments in the universe. Other stars won't be so fortunate. The changing gravitational field will destabilize their orbits, sending some plunging directly into one of the black holes while flinging others into highly elliptical trajectories that alternately carry them close to the black holes and far out into the merged galaxy's halo. The black holes themselves will slowly spiral inward, their orbital energy dissipated through the emission of gravitational waves. This process could take millions of years, during which the black hole binary will be one of the most powerful sources of gravitational radiation in the universe. When they finally merge, the resulting explosion of gravitational waves will be so intense it could be detected by instruments in distant galaxy clusters. The merged black hole, containing roughly 104 million solar masses, will be one of the most massive objects in our local cosmic neighborhood. It will dominate the gravitational dynamics of the merged galaxy for billions of years, continuing to shape the motion of stars and gas in the central regions long after the initial violence of the merger has subsided. But the collision won't just be destructive. The gravitational chaos will compress vast regions of gas and dust, triggering the most intense episode of star formation that either galaxy has experienced in billions of years. This starburst phase will light up the merging system with the births of millions of massive, luminous stars. The rate of star formation during the merger will be roughly 10 to 100 times higher than the current rate in either galaxy. This means that in just a few 100 million years, the merging system will produce more new stars than the Milky Way has created in the past several billion years. The energy output from all these young, hot stars will make the merged galaxy one of the brightest objects in the local universe. However, this burst of creativity will be short-lived on cosmic timescales. The merger will consume most of the available gas and dust in both galaxies, leaving little raw material for future star formation. After the initial starburst fades, the merged galaxy will settle into a much quieter phase, forming new stars at a rate far below what we see in spiral galaxies today. The structure of the merged galaxy will be completely transformed. Both the Milky Way and Andromeda are currently spiral galaxies with organized disk structures and well-defined spiral arms. But galaxy mergers tend to destroy these delicate structures, randomizing stellar orbits and creating more spherical, elliptical configurations. The final product of the Andromeda-Milky Way merger will be a giant elliptical galaxy, which astronomers have already nicknamed Milkomeda or Milkdromeda. This new galaxy will be larger than either of its parents, containing the combined stellar populations of both systems plus all the new stars born during the merger process. Elliptical galaxies have very different properties from spiral galaxies. They lack the organized rotation of spiral systems, instead containing stars that move in random, three-dimensional orbits. They typically have little ongoing star formation, appearing redder and more uniform than the blue spiral arms and dust lanes that characterize galaxies like the current Milky Way and Andromeda. But what does this cosmic catastrophe mean for our solar system and any life that might still exist in either galaxy when the collision occurs? The answer depends critically on the specific trajectory our solar system follows during the merger, and this is where the story becomes both fascinating and uncertain. Computer simulations suggest that our solar system has roughly equal chances of ending up in 3 different environments after the merger. About 1/3 of simulations show our Sun and its planets settling into the main body of the merged elliptical galaxy, probably in a region comparable to where we are now. Another third predict that we'll end up in the outer regions of Andromeda, farther from the galactic center than our current location. But the most intriguing possibility is represented by the final third of simulations. Our solar system could be ejected from the galaxy entirely. During the chaotic gravitational interactions of the merger, some stellar systems get accelerated to such high velocities that they escape from the merged galaxy altogether, becoming part of the intergalactic medium that exists between galaxy clusters. While this might sound catastrophic, it could actually provide a unique vantage point for studying the universe. Free from the dust and gas that obscures our view from within the galactic disk, an ejected solar system would have an unobstructed view of the cosmos. Future astronomers, if they exist, would be able to observe the cosmic microwave background radiation with unprecedented clarity and study distant galaxies without interference from local stellar sources. Here's a thought experiment that illustrates this possibility. Imagine you've been living your entire life in a house with frosted windows. You can see light and shadows, but everything outside is blurry and indistinct. Suddenly, you're transported to a glass house on a mountaintop with perfectly clear views in every direction. That's what it might be like for an ejected solar system, suddenly having access to an unobstructed view of the entire universe. Moreover, an ejected solar system would be relatively safe from most cosmic catastrophes. Supernovae, gamma-ray bursts, and other high-energy events that pose threats to life within galaxies would be much rarer in the intergalactic medium. The main challenge would be the extreme isolation, as any civilization that developed interstellar travel would find themselves trillions of miles from the nearest neighboring star systems. For stellar systems that remain within Andromeda, the merger will create both challenges and opportunities. The disruption of galactic structure will redistribute stellar populations, potentially bringing our solar system into contact with stars and planetary systems from completely different regions of the original galaxies. This mixing could have profound implications for the spread of life throughout the merged galaxy. If life exists in both the Milky Way and Andromeda, the merger will bring these separate biospheres into contact for the first time in their evolutionary histories. Organic molecules, primitive life forms, or even evidence of past civilizations could be exchanged between stellar systems that were previously separated by millions of light years. Imagine if you could somehow take samples from every ecosystem on Earth and mix them together in a giant laboratory. Species that had never encountered each other would suddenly find themselves sharing the same environment. Some might compete, some might cooperate, and entirely new forms of life might emerge from the interaction. The galactic merger could create similar opportunities for biological or technological exchange on a cosmic scale. The merger might also create entirely new environments for life to develop. The compression of gas and dust during the collision will trigger star formation in regions where it might not have occurred otherwise, creating new planetary systems in parts of the galaxy that were previously barren. Some of these new worlds might form under conditions that are impossible in present-day galaxies, potentially leading to exotic forms of life adapted to unusual stellar environments. But the collision will also pose significant challenges for any existing life. The increased density of stars in the merged galaxy will result in more frequent close encounters between stellar systems. These encounters can disrupt planetary orbits, potentially ejecting worlds from their solar systems or sending them into eccentric orbits that alternate between scorching heat and frozen cold. The enhanced supernova rate during the starburst phase will flood large regions of the galaxy with harmful radiation. Worlds that are currently safely nestled in their stars' habitable zones might find themselves sterilized by gamma-ray bursts or stripped of their protective atmospheres by intense stellar winds from nearby massive stars. Yet life has proven remarkably resilient throughout Earth's history, surviving multiple mass extinctions and adapting to changing conditions over billions of years. If life exists elsewhere in either galaxy, it might prove equally adaptable to the challenges posed by galactic merger. Some organisms might even thrive in the new environments created by the collision, diversifying and spreading throughout the merged system. The merger will also have profound effects on the large-scale structure of our local cosmic neighborhood. The local group of galaxies, which currently includes the Milky Way, Andromeda, and dozens of smaller companions, will be fundamentally altered. Many of the dwarf galaxies that currently orbit the Milky Way and Andromeda will be disrupted or absorbed during the merger, while others might be flung out of the system entirely. The gravitational dynamics of the entire local group will shift as the merged Andromeda Galaxy becomes the dominant gravitational influence in the region. This could affect the orbits of more distant galaxies, potentially triggering additional mergers or interactions over even longer timescales. But the Andromeda-Milky Way collision is just one event in a much larger cosmic drama. Galaxy mergers are common throughout the universe, and they play crucial roles in the formation and evolution of galactic structure. By studying our own impending merger in detail, astronomers are gaining insights into processes that have shaped the universe for billions of years. Computer simulations of the collision have revealed that galaxy mergers are far more complex than initially imagined. The process doesn't simply involve two galaxies coming together and settling into a new configuration. Instead, the systems can undergo multiple encounters, separating and reapproaching several times before finally merging completely. During these repeated encounters, tidal forces strip away material from both galaxies, creating complex structures of stellar streams and debris that can persist for billions of years after the main merger event. These tidal features preserve archaeological evidence of the collision, allowing future astronomers to reconstruct the merger history long after the original galactic structures have been completely transformed. Here's an analogy that captures this complexity. Imagine two dancers performing an elaborate routine where they repeatedly approach each other, spin around each other, separate, and come back together. Each time they interact, pieces of their costumes get torn away and scattered around the dance floor. The final dance might last only a few minutes, but the debris field preserves evidence of every interaction that occurred during the performance. The Andromeda-Milky Way collision will also provide the first opportunity to study a major galaxy merger from the inside. All previous observations of galaxy collisions have been made from external vantage points, often billions of light years away. When our galaxies merge, any surviving civilizations will have front-row seats to witness phenomena that can currently only be studied through distant observations and computer simulations. This inside perspective could reveal new physics and provide tests of our understanding of galactic dynamics, stellar evolution, and gravitational interactions. The merger might uncover exotic objects or processes that are invisible in distant galaxy collisions, advancing our knowledge of how the universe works on the largest scales. The collision will also offer unique opportunities to study dark matter, the mysterious invisible substance that makes up most of both galaxies' mass. During the merger, the dark matter halos of the two galaxies will interact in complex ways, potentially creating observable effects that could reveal new information about dark matter's properties. Unlike the stars and gas in the galaxies, which can collide and interact electromagnetically, dark matter particles are thought to interact only gravitationally. This means that the dark matter components of the two galaxies might pass through each other relatively unimpeded, creating temporary separations between the dark matter and normal matter components of the merged system. Such separations have been observed in distant galaxy cluster collisions and provide some of the strongest evidence for dark matter's existence. The Andromeda-Milky Way merger will offer a chance to study these effects in unprecedented detail, potentially revealing whether dark matter has any interactions beyond gravity. The merger timeline also raises fascinating questions about the ultimate fate of cosmic structure. The collision is occurring during an epoch when the universe's expansion is accelerating due to dark energy. This acceleration is gradually pulling galaxy clusters apart, making future mergers increasingly unlikely. The Andromeda Milky Way collision might be one of the last major galaxy mergers that will occur in our local cosmic neighborhood. Future civilizations in Milkomeda will look out into a universe where other galaxies have been carried so far away by cosmic expansion that they've disappeared beyond the cosmic horizon, leaving the merged galaxy as an island universe in an increasingly empty cosmos. This isolation will have profound implications for any advanced civilizations that might exist in the distant future. Without access to other galaxies, they'll be limited to the resources available within their own merged system. The finite number of stars and planets in Milkomeda will represent the absolute limit of available cosmic real estate, making efficient use of galactic resources a matter of ultimate importance. But that future is still inconceivably distant. The collision timeline of 4.5 billion years is longer than the entire history of complex life on Earth. If humanity survives and continues to develop technologically, we might have capabilities by then that are as far beyond our current understanding as our technology is beyond that of primitive bacteria. Such advanced civilizations might be able to influence or even control the merger process, using their mastery of physics and engineering to guide the collision in directions that serve their purposes. They might preserve certain stellar systems from disruption, create artificial star formation regions, or even manipulate the trajectories of the supermassive black holes themselves. More speculatively, truly advanced civilizations might use the energy released during the collision to power projects of unimaginable scope. The gravitational waves emitted by the merging black holes represent enormous amounts of energy that could theoretically be harvested and utilized. The starburst phase could provide the raw materials for constructing megastructures on galactic scales. But even if no advanced civilizations exist to witness or influence the merger, the collision will represent one of the most significant events in the history of our local universe. It will mark the end of an era that began billions of years ago, when the first galaxies formed from primordial gas and dark matter, and the beginning of a new phase of cosmic evolution dominated by merged systems and increasing isolation. The Andromeda Milky Way collision thus serves as both an ending and a beginning, the culmination of billions of years of galactic evolution and the starting point for entirely new forms of cosmic structure. It reminds us that even the largest and most permanent-seeming features of the universe are temporary, subject to change and transformation over sufficiently long timescales. As we continue to study Andromeda and prepare for this distant but inevitable collision, we're reminded that we're witnessing a process that connects the smallest scales of physics to the largest structures in the cosmos. The merger will be driven by the same gravitational forces that keep planets in orbit around stars, but operating on scales so vast that the entire event will take longer than complex life has existed on Earth. Understanding this collision requires us to think beyond human timescales and consider processes that unfold over geological and cosmic epochs. It challenges us to imagine futures so distant that they might as well be alternate realities, yet they're as inevitable as sunrise and sunset. The collision course with Andromeda thus represents more than just an astronomical curiosity. It's a window into the deep future of our cosmic neighborhood and a reminder that we're part of a universe that's constantly changing and evolving on scales far larger than anything in human experience. As we look forward to this cosmic convergence, we're confronting questions about the ultimate fate of galaxies, stars, planets, and possibly life itself in an evolving universe. Andromeda isn't just a galaxy filled with stars and planets. It's a cosmic laboratory where the most extreme physics in the universe plays out on scales so vast they challenge our most fundamental theories about the nature of reality itself. Within its depths, matter exists in states so exotic that they bend and warp the very fabric of space and time. Energy densities reach levels that dwarf anything we can create on Earth, and gravitational fields become so intense that they literally rewrite the rules of physics as we understand them. To study Andromeda is to peer into realms where Einstein's theories of relativity are pushed to their absolute limits, where quantum mechanics meets cosmology in ways that reveal deep connections between the smallest and largest scales in nature, and where phenomena occur that shouldn't be possible according to our current understanding of how the universe works. Consider what happens in the immediate vicinity of Andromeda's central supermassive black hole, M31. Here, in a region smaller than our solar system, 100 million times the mass of our Sun is compressed into a gravitational singularity so dense that our current physics simply breaks down. The event horizon surrounding this monster has a circumference of roughly 2.6 billion kilometers, large enough that light would take over 2 hours to travel around it. But it's not just the black hole's enormous mass that makes it fascinating from a physics perspective. It's the way this mass warps space and time itself, creating effects that seem like science fiction but are actually fundamental features of Einstein's general theory of relativity played out on cosmic scales. Time dilation around M31 is so extreme that clocks would run measurably slower near the black hole than they do in the outer regions of the galaxy. An astronaut falling toward the event horizon would experience time passing normally for herself, but to outside observers, her descent would appear to slow down dramatically as she approached the point of no return. From the perspective of the distant galaxy, she would appear to freeze at the event horizon, her image becoming increasingly redshifted until it faded from view. But here's where the physics becomes truly mind-bending. The astronaut herself would experience something completely different. As she crossed the event horizon, she would find herself in a region of space-time so severely curved that the normal concepts of past and future lose their meaning. The center of the black hole wouldn't be a place she could reach in space, but rather a moment in her future that she would inevitably encounter regardless of any action she might take. These aren't just theoretical possibilities. The gravitational field around M31 is so intense that its effects can be observed in the behavior of stars orbiting the black hole at distances of light years. These stars follow elliptical orbits that precess or rotate in ways that precisely match Einstein's predictions about how matter moves in severely curved space-time. The study of these orbital motions provides one of the most precise tests of general relativity available anywhere in the universe. The deviations from Newtonian orbital mechanics are tiny but measurable, confirming that space and time really do behave as Einstein predicted even under the most extreme gravitational conditions we can observe. But M31 represents just one example of how Andromeda serves as a laboratory for extreme physics. Throughout the galaxy, neutron stars create conditions that push matter itself to its absolute limits. The cores of these objects reach densities where atomic nuclei are literally crushed together, creating forms of matter that can't exist anywhere else in the current universe. At these extreme densities, the normal properties of matter begin to break down. Protons and neutrons might merge into exotic particles called hyperons or delta baryons. The electromagnetic forces that normally keep atomic nuclei apart are overwhelmed by gravitational compression, allowing matter to exist in configurations that would be impossible under ordinary conditions. Some theoretical physicists have proposed that the cores of the most massive neutron stars might undergo a phase transition to an even more exotic state called quark matter, where the normal structure of protons and neutrons dissolves entirely, leaving behind a soup of their constituent quarks. If such quark stars exist in Andromeda, they would represent the most extreme form of matter possible short of a black hole. Here's a thought experiment that illustrates just how extreme these conditions are. Imagine trying to compress all the people on Earth into a space the size of a sugar cube. That's roughly equivalent to the density in the core of a neutron star. Under such conditions, the normal rules of chemistry and atomic physics simply don't apply. Matter is forced into states that are completely foreign to our everyday experience. The magnetic fields around Andromeda's neutron stars create their own exotic physics. The strongest magnetic fields in the galaxy, found around magnetars, are so intense they fundamentally alter the structure of empty space itself. In such fields, the quantum vacuum becomes birefringent, meaning it affects light differently depending on the photon's polarization. These effects, predicted by quantum electrodynamics but impossible to observe under terrestrial conditions, turn neutron stars into natural laboratories for studying how electromagnetic fields interact with the quantum structure of space-time. The fact that we can observe these effects in Andromeda provides confirmation that our understanding of quantum field theory remains valid even under the most extreme conditions imaginable. But perhaps the most mind-bending physics in Andromeda involves the interplay between quantum mechanics and general relativity near black holes and neutron stars. According to quantum theory, empty space isn't really empty, but is filled with virtual particle pairs that constantly appear and disappear. Near the event horizon of a black hole, these quantum fluctuations can become real particles through a process called Hawking radiation. The theory predicts that black holes should slowly evaporate by emitting these quantum particles, with the evaporation rate inversely related to the black hole's mass. For supermassive black holes like M31, this process is extraordinarily slow, taking far longer than the current age of the universe to have any noticeable effect. But the mere fact that quantum mechanics predicts black holes should evaporate at all represents a profound connection between gravity and quantum theory that we're still trying to fully understand. The information paradox associated with Hawking radiation is one of the deepest unsolved problems in theoretical physics. If black holes evaporate completely, what happens to the information about all the matter that fell into them? Quantum mechanics insists that information cannot be destroyed, but general relativity suggests that anything crossing a black hole's event horizon is lost forever. Proposed solutions to this paradox range from modifications to general relativity to radical reinterpretations of what information means in quantum theory. Some physicists have suggested that the information is encoded on the black hole's event horizon surface, creating a holographic representation of everything that has fallen in. Others propose that information might escape through quantum entanglement between particles inside and outside the black hole. Studying supermassive black holes like M31 provides crucial observational tests for these theories. The way matter behaves as it approaches the event horizon, the properties of the radiation emitted by the accretion disk, and the gravitational wave signals produced when black holes merge all provide clues about which theoretical approaches might be correct. The recent detection of gravitational waves by observatories like LIGO and Virgo has opened up entirely new ways to study the extreme physics around black holes and neutron stars. When the supermassive black holes at the centers of Andromeda and the Milky Way eventually merge during the galactic collision, they will produce gravitational waves so powerful they could be detected by future space-based observatories from distances of billions of light years. These gravitational waves will carry detailed information about the merger process, including precise measurements of the black hole's masses, spins, and the dynamics of their final death spiral. By analyzing these signals, physicists will be able to test general relativity under conditions far more extreme than anything accessible through current observations. The waves themselves represent ripples in the fundamental structure of space-time, traveling at the speed of light and carrying energy away from the merging system. The fact that we can detect and measure these ripples confirms one of Einstein's most exotic predictions and provides a completely new way to study the universe. But gravitational waves from black hole mergers are just one example of how Andromeda helps us explore the frontiers of physics. The galaxy also serves as a natural particle accelerator, creating cosmic rays with energies far beyond anything achievable in terrestrial laboratories. The most energetic cosmic rays detected on Earth have energies exceeding 10,020 electron volts, roughly 10 million times higher than particles produced in the Large Hadron Collider. The sources of these ultra-high energy particles remain mysterious, but they likely involve the most extreme astrophysical environments in the universe, including the regions around supermassive black holes, magnetar surfaces, and the shock waves from supernova explosions. If such acceleration mechanisms operate in Andromeda, they would be producing particles with energies high enough to probe physics beyond the standard model of particle physics. These cosmic rays might carry information about exotic particles, extra dimensions, or other phenomena that can't be studied through any other means. Here's a way to visualize the extreme energies involved. If you could somehow concentrate all the kinetic energy of a baseball traveling at 100 mph into a single subatomic particle, you would still be far short of the energies carried by the most powerful cosmic rays. These particles pack the energy of macroscopic objects into spaces billions of times smaller than atomic nuclei. The study of cosmic rays also connects to one of the deepest mysteries in cosmology, the nature of dark matter. If dark matter is composed of weakly interacting particles, as many theories suggest, these particles might occasionally collide with high-energy cosmic rays, producing detectable signals that could reveal dark matter's properties. Andromeda's vast dark matter halo makes it an ideal laboratory for studying such interactions. The galaxy contains roughly 5 times more dark matter than normal matter, creating a dense environment where dark matter interactions, if they occur, would be more likely to produce observable effects. Some theoretical models predict that dark matter particles might annihilate when they encounter their antiparticles, producing gamma rays, neutrinos, or other detectable signals. The centers of galaxies, where dark matter densities are highest, would be the most promising locations to search for such annihilation signals. Advanced gamma-ray telescopes like the Fermi Large Area Telescope and the upcoming Cherenkov Telescope Array are sensitive enough to detect dark matter annihilation signals from Andromeda if the annihilation rates are high enough. The fact that no clear signals have been detected so far places important constraints on dark matter models, helping physicists narrow down the possibilities for what this mysterious substance might be. The search for dark matter also connects to efforts to understand the fundamental structure of space-time itself. Some theories propose that dark matter might be composed of particles that exist in extraspatial dimensions beyond the 3 we can observe directly. These hidden dimensions might be compactified or curled up on scales so small that we can't perceive them directly. If such extra dimensions exist, they might become accessible at very high energies or in regions of extremely curved spacetime like those found around black holes and neutron stars. The extreme gravitational fields in Andromeda might provide natural laboratories for studying physics in higher dimensions, potentially revealing new aspects of reality that are completely hidden under ordinary conditions. String theory, one of the most ambitious attempts to unify all the fundamental forces of nature, predicts that such extra dimensions should exist. But testing string theory through direct observation has proven extraordinarily difficult, partly because the energy scales involved are so much higher than anything accessible through current technology. The extreme environments around Andromeda's black holes and neutron stars might provide the only natural laboratories where string theory effects could be directly observed. The behavior of matter and energy in these regions might reveal signatures of extra dimensions, cosmic strings, or other exotic phenomena predicted by string theory, but undetectable under ordinary conditions. But perhaps the most profound way that Andromeda challenges our understanding of physics involves the fundamental nature of information and consciousness. If information is indeed a fundamental feature of reality, as suggested by developments in quantum theory and cosmology, then the complex structures we observe in Andromeda might represent vast information processing systems operating on scales we can barely comprehend. The galaxy's spiral structure, for instance, might be more than just the result of gravitational forces and stellar dynamics. It could represent the physical manifestation of information flows, with matter and energy organized according to computational processes that operate on galactic scales and timescales. This perspective, while highly speculative, is grounded in serious research into the connections between physics and information theory. The holographic principle suggests that all the information contained in a 3-dimensional region of space can be encoded on its 2-dimensional boundary. If this principle applies to galaxies, then everything we observe in Andromeda's interior might be represented as patterns on some cosmic boundary we can't directly perceive. Even more speculatively, some physicists have proposed that consciousness itself might be a fundamental feature of reality, emerging wherever information processing reaches sufficient complexity. If this is true, then galaxies like Andromeda might not just contain consciousness, but might themselves be conscious entities, thinking thoughts on timescales of millions or billions of years. These ideas push far beyond current scientific consensus, but they illustrate how studying Andromeda forces us to confront fundamental questions about the nature of reality, information, and consciousness. The galaxy serves as a mirror that reflects our deepest assumptions about what the universe is and how it works. The observational techniques required to study Andromeda also push the boundaries of what's technologically possible. Measuring the properties of individual stars in another galaxy requires telescopes with unprecedented light-gathering power and angular resolution. Detecting gravitational waves from merging black holes requires instruments sensitive enough to measure changes in distance smaller than 1,000th of the width of a proton. The next generation of telescopes and instruments will push these capabilities even further. The James Webb Space Telescope can peer deeper into infrared wavelengths than any previous observatory, potentially revealing new details about Andromeda's stellar populations and chemical evolution. The upcoming Extremely Large Telescope will have a primary mirror 39 meters across, large enough to directly image some of the largest planets around Andromeda's nearest stars. Space-based gravitational wave observatories like the proposed LISA mission will be sensitive enough to detect the merger of supermassive black holes from cosmological distances, providing unprecedented insights into the physics of black hole formation and evolution. Advanced neutrino detectors might eventually be able to detect high-energy neutrinos from Andromeda, opening up entirely new ways to study stellar explosions and other energetic processes. But perhaps the most revolutionary developments will come from techniques we haven't yet invented. The history of astronomy is filled with discoveries that became possible only after new technologies were developed, from Galileo's telescope to radio astronomy to gravitational wave detection. Future breakthroughs in quantum sensing, artificial intelligence, or even more exotic technologies might reveal aspects of Andromeda that are currently unimaginable. The study of Andromeda also connects to some of the deepest philosophical questions about the nature of scientific knowledge. How can we be confident that the physical laws we observe operating in our local environment apply to conditions billions of times more extreme than anything we can create on Earth? What does it mean to understand phenomena that operate on scales of space and time so vast they dwarf human experience? These questions become particularly acute when we consider the possibility that our understanding of physics itself might be incomplete or incorrect in ways we haven't yet recognized. The history of science is filled with revolutionary discoveries that overturned previously accepted theories, from quantum mechanics to relativity to the expanding universe. Studying extreme environments like those found in Andromeda provides crucial tests for our current theories and might reveal phenomena that point toward new physics. The fact that general relativity and quantum mechanics have been so successful in explaining observations of distant galaxies is remarkable, but it doesn't guarantee that these theories will continue to work under even more extreme conditions. Some physicists have proposed that the apparent accelerated expansion of the universe attributed to dark energy might actually be evidence that general relativity breaks down on cosmological scales. Others have suggested that the dark matter problem might be solved by modifications to our understanding of gravity rather than by invoking exotic new particles. Testing these alternatives requires observations of systems like Andromeda, where gravitational effects operate on scales intermediate between solar systems and the entire observable universe. The galaxy serves as a natural laboratory for studying gravity under conditions that can't be replicated through any other means. The extreme physics in Andromeda also raises questions about the ultimate limits of knowledge and observation. Black holes create regions of space-time that are causally disconnected from the rest of the universe, meaning that no information about what happens inside them can ever reach outside observers. This creates fundamental limits on what we can know about the universe, regardless of how advanced our technology becomes. Similarly, the finite speed of light means that we can never observe Andromeda as it exists now, but only as it was 2.5 million years ago. If the galaxy harbors advanced civilizations or undergoes rapid changes, we might be forever unable to detect them due to the fundamental limitations imposed by the structure of space-time itself. These limits on observation and knowledge connect to deep questions in philosophy of science about the relationship between reality and our ability to understand it. Is the universe fundamentally comprehensible, or are there aspects of reality that will forever remain beyond human understanding? The study of Andromeda doesn't provide definitive answers to these questions, but it does illustrate both the remarkable power and the fundamental limitations of scientific inquiry. The galaxy serves as a reminder that we live in a universe far stranger and more wonderful than our everyday experience might suggest, but also far more mysterious than our current theories can fully explain. As we continue to study Andromeda with ever more sophisticated instruments and techniques, we're likely to discover new phenomena that challenge our understanding of physics in ways we can't currently imagine. The galaxy will continue to serve as a laboratory for testing the limits of our knowledge and pushing the boundaries of what's possible in science and technology. But perhaps the most important lesson Andromeda teaches us is about the provisional nature of scientific knowledge. Every theory, no matter how successful, is subject to revision or replacement in light of new observations. The galaxy reminds us that science is not a fixed body of knowledge, but an ongoing process of discovery and refinement. In this sense, Andromeda represents both a destination and a journey, both an object of study and a mirror that reflects our own intellectual limitations and aspirations. As we probe its mysteries, we're simultaneously exploring the frontiers of human knowledge and confronting the fundamental questions about reality that have driven scientific inquiry for centuries. The physics at play in Andromeda connects the smallest scales of quantum mechanics to the largest scales of cosmology, revealing deep relationships between phenomena that might otherwise seem completely unrelated. In studying this galaxy, we're not just learning about a distant collection of stars and gas. We're exploring the fundamental principles that govern all of reality, from the quantum vacuum to the cosmic web of galaxies that spans the observable universe. When you look at Andromeda, you're not just seeing a galaxy as it exists in a single moment. You're witnessing the culmination of over 10 billion years of cosmic evolution, a story written in starlight that spans nearly 3/4 of the universe's entire history. Every photon that reaches your eye has traveled across space for 2.5 million years, but the processes that created those photons began when the cosmos was barely a quarter of its current age. This perspective transforms Andromeda from a static object into a dynamic chronicle of cosmic development, a fossil record preserved in light that documents how the universe has changed and evolved since shortly after the first stars began to shine. But to truly understand what we're seeing requires us to think on timescales so vast they challenge human comprehension, scales where millions of years become mere moments and the entire history of human civilization disappears into statistical noise. The story begins roughly 13 billion years ago, when the universe had cooled sufficiently from the Big Bang for the first atoms to form. At this point, space was filled with a nearly uniform sea of hydrogen and helium, with tiny density fluctuations that would eventually grow into the cosmic web of structure we see today. The seeds of galaxies like Andromeda were already present in these primordial variations, invisible ripples in the fabric of space-time that would slowly grow under the influence of gravity. But the universe of 13 billion years ago bore no resemblance to the cosmos we observe today. There were no stars, no planets, no heavy elements, no complex chemistry. The night sky, had there been anyone to observe it, would have been completely dark. The only light came from the fading afterglow of creation itself, the cosmic microwave background radiation that still permeates space today, but has been stretched and cooled by billions of years of cosmic expansion. Here's a thought experiment that puts this early universe in perspective. Imagine a vast, dark ocean with no islands, no life, no features of any kind except for tiny ripples on the surface. Those ripples are so small they're barely detectable, but over enormous spans of time they will grow into massive waves, then towering mountain ranges, and eventually entire continents. That's essentially what happened in the early universe. Microscopic fluctuations eventually became galaxies, stars, and everything we see today. The first structures to condense out of this primordial soup were not galaxies as we know them today, but much smaller objects, proto-galactic fragments containing perhaps a few million times the mass of our Sun. These early systems were dominated by dark matter, the invisible scaffolding that provided the gravitational framework for all subsequent structure formation. Within these dark matter halos, the first stars began to form roughly 13.5 billion years ago, perhaps 200 million years after the Big Bang. These population third stars were unlike anything that exists in the current universe. They were composed almost entirely of hydrogen and helium, lacking the heavy elements that play crucial roles in modern star formation. As a result, they could grow to enormous sizes, possibly hundreds of times more massive than our Sun. The lives of these primordial giants were spectacular but brief. Within just a few million years, they exhausted their nuclear fuel and exploded as hypernovae, stellar detonations so powerful they could sterilize entire proto-galaxies with their radiation. But these explosions served a crucial purpose in cosmic evolution. They scattered the first heavy elements throughout the early universe, seeding space with the carbon, oxygen, nitrogen, and iron that would eventually make planets and life possible. Think about what this means. Every heavy element in your body was forged in the core of a star that died billions of years before our solar system even existed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was manufactured by the first generation of stars and scattered across the cosmos by their explosive deaths. The remnants of population 3 stars also left behind the first black holes, gravitational monsters that would eventually grow to become the supermassive black holes found at the centers of present-day galaxies. The connection between these early stellar mass black holes and today's supermassive giants remains one of the great mysteries in astronomy, but it likely involved a complex process of mergers and accretion that paralleled the growth of galaxies themselves. By about 12 billion years ago, roughly 1.8 billion years after the Big Bang, the first recognizable galaxies had begun to form. These early systems were much smaller and more chaotic than modern galaxies like Andromeda, but they established the basic pattern of galactic evolution that continues today. Gas collapses under gravity to form stars. Stars synthesize heavy elements and disperse them through stellar winds and explosions, and the enriched material serves as the raw material for new generations of stars and planets. The early universe was a much more violent and chaotic place than the relatively sedate cosmos we observe today. Galaxy collision rates were hundreds of times higher, star formation rates were much more intense, and the background radiation levels were sufficient to ionize most of the hydrogen in intergalactic space. In this environment, any life that might have developed would have faced challenges far more severe than anything terrestrial organisms have ever encountered. But this cosmic violence was also creative. The high collision rates meant that small proto-galaxies were constantly merging to form larger systems. Each merger brought together the stellar populations, gas reserves, and heavy element inventories of the merging systems, gradually building up the massive galaxies we see in the present-day universe. Andromeda's own formation history exemplifies this hierarchical assembly process. Computer simulations suggest that the galaxy we see today is the result of hundreds or perhaps thousands of smaller mergers that occurred over billions of years. Each collision added mass and complexity to the growing system, while also triggering intense episodes of star formation that rapidly enriched the interstellar medium with heavy elements. The evidence for this merger history is written throughout Andromeda's current structure. The stellar streams visible in the galaxy's outer halo are the stretched-out remnants of dwarf galaxies that were torn apart by tidal forces during past encounters. The chemical composition of stars in different regions reflects the varying conditions under which they formed, preserving information about the galaxy's assembly history like layers of sediment in a geological formation. But galactic evolution involves more than just the accumulation of mass through mergers. The internal processes within galaxies also play crucial roles in shaping their development over cosmic time. Star formation, stellar evolution, and stellar death create complex feedback loops that regulate how galaxies grow and change. When massive stars explode as supernovae, they don't just enrich the interstellar medium with heavy elements. They also inject enormous amounts of energy into the surrounding gas, heating it and sometimes driving it completely out of the galaxy. This process, known as galactic winds or outflows, can shut down star formation for millions of years and significantly affect the galaxy's future evolution. Here's an analogy for this feedback process. Imagine a city where every new building that gets constructed occasionally explodes, scattering debris and energy throughout the neighborhood. Sometimes, these explosions are so powerful they drive residents out of entire districts, leaving them uninhabitable for years. That's essentially what happens in galaxies. Stellar explosions can shut down star formation in large regions for extended periods. The supermassive black holes at galactic centers also play important regulatory roles. When these monsters actively accrete matter, they can produce jets and radiation so intense that they heat the surrounding gas and prevent it from collapsing to form new stars. This AGN feedback appears to be crucial for understanding why the most massive galaxies in the present-day universe have relatively low star formation rates. Andromeda shows clear evidence of both supernova feedback and AGN feedback in its structure and stellar populations. The galaxy's current star formation rate is much lower than what we might expect based on its gas content, suggesting that feedback processes have been effective at regulating stellar birth. The central black hole M31 appears to be in a relatively quiescent state, but evidence suggests it was much more active in the past. The interplay between these various feedback mechanisms creates a complex evolutionary history that unfolds over billions of years. Galaxies don't simply grow steadily larger and more massive. Instead, they experience periods of intense activity alternating with quieter phases, creating a punctuated evolutionary pattern that depends on both internal processes and external influences like major mergers. Understanding this evolutionary history requires us to think about time on scales that dwarf human experience. The formation of a single generation of stars, from the initial collapse of a gas cloud to the final supernova explosion of the most massive stars, takes roughly 50 million years. But galaxy evolution involves hundreds or thousands of such stellar generations, each one building on the chemical and dynamical legacy of its predecessors. The concept of deep time becomes even more profound when we consider that we're observing Andromeda not as it exists today, but as it was 2.5 million years ago. The light we see left the galaxy when our own ancestors were just learning to use stone tools. If there are advanced civilizations in Andromeda, they might have risen and fallen in the time it has taken their light to reach us. This temporal disconnect raises fascinating questions about the nature of observation and knowledge on cosmic scales. We can never observe the current state of distant galaxies, only their past conditions. As we look deeper into space, we're also looking further back in time, seeing the universe as it existed during earlier epochs of cosmic evolution. The most distant galaxies we can observe appear as they were when the universe was less than 1 billion years old, still in its infancy compared to the 13.8 billion year age we measure today. These ancient systems show us what the early stages of galactic evolution looked like, providing crucial constraints on our theoretical models of cosmic structure formation. By comparing galaxies at different distances, and therefore different cosmic epochs, astronomers can reconstruct the history of galactic evolution over most of the universe's lifetime. This archaeological approach reveals that galaxies like Andromeda have changed dramatically over cosmic time, growing in mass, evolving chemically, and developing the complex structures we observe today. The rate of cosmic evolution itself has changed over time. The early universe evolved much more rapidly than the current epoch, with major transformations occurring over relatively short periods. Star formation rates peaked roughly 10 to 11 billion years ago and have been declining ever since. The merger rates between galaxies have also decreased significantly as cosmic expansion has carried systems farther apart. This deceleration of cosmic evolution reflects the universe's gradual transition from a dense, rapidly evolving state to the more sparse and sedate cosmos we observe today. The period when Andromeda was assembling its current mass through mergers was also the era when cosmic evolution was proceeding most rapidly. But the story of cosmic evolution extends far beyond the formation and growth of individual galaxies. The universe as a whole has been undergoing profound changes that affect the environments in which galaxies develop. The discovery of dark energy and the accelerating expansion of the universe suggests that we're entering a new phase of cosmic evolution that will ultimately determine the fate of all cosmic structure. As the universe continues to expand and accelerate, the large-scale structure that currently connects galaxies through the cosmic web will gradually dissolve. Galaxy clusters will become increasingly isolated, and eventually even bound systems like our local group will find themselves alone in an ever-expanding ocean of space. This cosmic perspective transforms our understanding of Andromeda's significance. The galaxy isn't just a collection of stars and gas, it's a participant in a cosmic drama that has been unfolding for nearly the entire history of the universe. Its formation, evolution, and eventual merger with the Milky Way are all chapters in a much larger story of how complexity and structure emerge, flourish, and eventually fade in an expanding cosmos. The chemical evolution of Andromeda also connects to broader questions about the development of complexity in the universe. The galaxy has served as a factory for producing heavy elements, transforming the simple hydrogen and helium of the early universe into the rich periodic table of elements we observe today. Every carbon atom, every oxygen molecule, every grain of cosmic dust represents a step in the universe's ongoing evolution toward greater chemical complexity. This chemical evolution has profound implications for the potential development of life. The early universe lacked the elements necessary for complex chemistry and life as we know it. Only after billions of years of stellar nuclear synthesis did the cosmos develop the chemical diversity needed for planets, organic molecules, and potentially biological systems. Andromeda's role in this chemical evolution extends beyond just producing heavy elements. The galaxy's mergers and interactions have mixed materials that formed under different conditions, creating opportunities for novel chemical processes and combinations that might not have occurred in more isolated systems. The distribution of elements throughout Andromeda also tells a story about how chemical evolution proceeds on galactic scales. Elements are not uniformly distributed throughout the galaxy, but show systematic variations that reflect the history of star formation and mixing processes. Understanding these chemical patterns provides insights into how the raw materials for planets and life are distributed throughout the cosmos. But perhaps the most profound aspect of Andromeda's evolutionary story is what it reveals about the nature of time itself on cosmic scales. Human experience is dominated by timescales ranging from seconds to decades, with historical awareness extending back at most a few thousand years. Galactic evolution operates on timescales millions of times longer, where entire civilizations could rise and fall in periods that represent mere fluctuations in stellar evolution. This vast difference in timescales creates a fundamental challenge for understanding our place in the cosmic order. We exist as brief perturbations in processes that operate on scales far beyond human experience or control. Yet paradoxically, we've developed the intellectual tools to comprehend and study these processes, making us perhaps the only known entities capable of understanding cosmic evolution from the inside. The study of Andromeda thus becomes a meditation on the nature of time, change, and permanence in the universe. The galaxy appears stable and eternal from our perspective, but we know it's actually a dynamic, evolving system that has changed dramatically over its lifetime and will continue to change in the future. This temporal perspective also affects how we think about the search for life and intelligence in the universe. If advanced civilizations exist in Andromeda, they've had potentially billions more years than life on Earth to develop and evolve. The gap between their capabilities and our own might be so vast that we wouldn't recognize their activities as artificial even if we were observing them directly. Such civilizations might have transcended the physical limitations that constrain biological beings, existing as patterns of information that persist over cosmic timescales. They might manipulate matter and energy on galactic scales, orchestrating processes that appear to us as natural evolution, but are actually the products of intelligence operating on scales we can't comprehend. The possibility that what we interpret as natural galactic evolution might actually include artificial components raises profound questions about the relationship between intelligence and cosmic development. If consciousness and intelligence are fundamental features of the universe rather than rare accidents, then the evolution of galaxies like Andromeda might be guided by forms of awareness that operate on spatial and temporal scales beyond our current understanding. These speculative possibilities illustrate how the study of deep time and cosmic evolution pushes us toward questions that lie at the boundaries between science and philosophy. The vast timescales involved in galactic evolution force us to confront fundamental questions about causation, purpose, and meaning in a universe where human existence occupies an almost infinitesimally small fraction of cosmic history. Yet despite these overwhelming scales, there are also profound connections between galactic evolution and the development of complexity on much smaller scales. The chemical elements produced by stellar nucleosynthesis in galaxies like Andromeda are the same elements that make up our bodies and enable the complex chemistry of life. The energy sources that power galactic evolution also provide the stable environments necessary for biological evolution to proceed. In this sense, we are not separate from galactic evolution, but products of it. The atoms in our bodies were forged in stellar furnaces, possibly billions of years ago, mixed and redistributed through galactic mergers and stellar explosions, and eventually incorporated into the solar system, where they became part of living organisms capable of contemplating their own cosmic origins. The story of Andromeda is thus intimately connected to our own story, despite the vast differences in scale and timescale involved. The galaxy's 10 billion-year evolutionary history has produced the conditions that made our existence possible, while our ability to study and understand that history represents perhaps the universe's first opportunity to examine its own development through the lens of conscious awareness. This reflexive relationship between observer and observed adds another layer of complexity to the study of cosmic evolution. We are not external observers studying galactic development from the outside, but participants in the same cosmic processes we're trying to understand. Our observations and theories about galactic evolution are themselves products of that evolution, creating a kind of cosmic recursion that challenges traditional distinctions between subject and object. The implications extend far beyond astronomy and cosmology. If consciousness and intelligence are natural products of cosmic evolution, then the development of science and our ability to understand the universe represents a new phase in cosmic development itself. The universe, through beings like ourselves, has developed the capacity for self-awareness and self-understanding. From this perspective, the study of Andromeda becomes more than just an exercise in gathering information about a distant galaxy. It represents the universe's ongoing effort to understand itself, to trace the connections between past and future, and to comprehend the deep patterns that govern cosmic development over the largest possible scales. As we continue to probe Andromeda's secrets with ever more sophisticated instruments and techniques, we're simultaneously advancing our understanding of cosmic evolution and participating in that evolution ourselves. Each new discovery adds to the universe's growing knowledge about its own structure and history, creating an ever-expanding web of understanding that connects the smallest scales of quantum mechanics to the largest scales of cosmic structure. The galaxy that we see glowing in the constellation Andromeda is thus far more than a collection of stars and gas separated from us by millions of light-years of empty space. It's a participant in the same cosmic story that produced us, a chapter in the universe's ongoing evolution toward ever greater levels of complexity, organization, and possibly consciousness. The deep time perspective that emerges from studying Andromeda reminds us that we exist at a unique moment in cosmic history, when the universe has evolved sufficient complexity to become aware of itself, but still retains the diversity and dynamism necessary for continued development. We are witnesses to cosmic evolution, products of that evolution, and potentially agents capable of influencing its future direction. This realization transforms how we think about humanity's place in the cosmic order and our responsibilities as conscious beings in an evolving universe. The knowledge we gain about galaxies like Andromeda becomes part of the universe's growing understanding of itself, contributing to a cosmic self-awareness that may represent the most significant development in the history of cosmic evolution since the formation of the first stars and galaxies themselves. As we reach the end of our journey through Andromeda's mysteries, we find ourselves confronting a profound paradox. This galaxy, racing toward us at 250,000 miles per hour across the cosmic void, seems simultaneously impossibly distant and intimately connected to our existence. Every atom in your body was forged in stellar furnaces, perhaps not unlike those burning in Andromeda's spiral arms. The same physical laws that govern the fusion reactions in our Sun also power the trillion stars of our galactic neighbor. The dark matter that holds Andromeda together may be the same mysterious substance that shapes the cosmic web throughout the observable universe. Yet for all these connections, Andromeda remains profoundly alien to human experience. Its spatial scales dwarf our comprehension. Its temporal rhythms unfold over billions of years. The extreme physics playing out in its depths operates under conditions so severe they challenge our most fundamental theories about reality. The potential life forms it might harbor could be so different from terrestrial biology that we wouldn't recognize them as living even if they were communicating directly with us. This tension between connection and alienation, between the familiar and the incomprehensible, captures something essential about humanity's relationship with the cosmos. We are simultaneously products of cosmic evolution and observers capable of understanding that evolution. We are made of stardust, yet we can study the stars. We are confined to a single planet, orbiting an ordinary star in an unremarkable galaxy, yet we can probe the mysteries of distant galaxies billions of light years away. Here's a thought that should fill you with wonder. The carbon atoms in your DNA, the oxygen atoms you're breathing right now, the calcium atoms in your bones, they may have been created in stars very similar to those burning in Andromeda right now. In a very real sense, we are cosmic cousins with any life that might exist in that distant galaxy, all of us children of the same stellar nurseries that have been manufacturing the elements of life for billions of years. The story of our growing understanding of Andromeda exemplifies this unique position. Just over a century ago, we didn't even know other galaxies existed. Today, we can map the distribution of dark matter in Andromeda's halo, predict the exact timeline of its collision with our own galaxy, and search for signs of life among its trillion stars. This represents one of the most dramatic expansions of knowledge in human history, comparable to the Copernican revolution or the discovery of evolution. But this knowledge comes with profound implications that extend far beyond astronomy. Understanding Andromeda forces us to confront fundamental questions about our place in an immense and ancient universe. It challenges us to think on scales that dwarf human experience and consider possibilities that stretch the boundaries of imagination. Consider what it means that we can predict the collision between Andromeda and the Milky Way with such precision. We are living beings, products of biological evolution on a single planet, yet we can forecast cosmic events that will occur billions of years in the future. This represents a form of temporal transcendence that is perhaps unique in the known universe. We exist in the present moment, but our minds can range across cosmic history and project into the deep future. This capability raises profound questions about the nature of consciousness and intelligence. Are we typical examples of what happens when matter and energy organize themselves into sufficiently complex patterns? Or are we rare anomalies, temporary fluctuations in an otherwise unconscious cosmos? The answer to this question could determine whether the universe is filled with intelligence or whether consciousness is a fleeting accident that will disappear when the last stars burn out. The search for life in Andromeda connects directly to these existential questions. If we find evidence of biology in our galactic neighbor, it would suggest that life is a natural and perhaps inevitable consequence of cosmic evolution. The universe would be revealed as inherently creative, constantly generating new forms of complexity and organization. Intelligence might be a fundamental feature of reality rather than a rare accident. But even if we never find definitive proof of life in Andromeda, the galaxy serves as a reminder of the vast possibilities that exist beyond our current understanding. With 1 trillion stars and potentially trillions of planets, Andromeda represents an almost infinite space of possibilities for the emergence of complexity, consciousness, and perhaps forms of existence we can't currently imagine. The approaching collision between our galaxies adds urgency to these questions. In roughly 4.5 billion years, assuming our species or its descendants survive that long, they will witness one of the most spectacular events in cosmic history. The merger will create new opportunities for complexity to emerge while potentially destroying others. It will mix stellar populations that have been evolving separately for billions of years, potentially bringing together different experiments in biological or technological development. But 4.5 billion years is a timescale that challenges human comprehension. It's longer than the entire history of complex life on Earth. It's roughly equivalent to the age of our solar system itself. Any civilization that exists during the collision will be as different from present-day humanity as we are from primordial bacteria. This temporal perspective highlights one of the most profound aspects of studying Andromeda. It forces us to think beyond the limitations of human lifespan and historical experience. The galaxy operates on timescales where entire species could evolve, develop technology, achieve transcendence, and fade into memory while contributing just a few pages to the ongoing story of cosmic evolution. Yet paradoxically, our fleeting existence has achieved something remarkable. In just a few centuries of scientific development, we've managed to decode many of Andromeda's secrets. We've traced its formation history, mapped its structure, and even predicted its ultimate fate. This represents a form of intellectual achievement that might be genuinely unique in the cosmos. Here's something that should make you pause and reflect. You, sitting here right now, know more about Andromeda than any human being who lived before the 20th century. You understand that it's a galaxy containing 1 trillion stars, that it's approaching our galaxy for an eventual collision, that it's dominated by mysterious dark matter. This knowledge, which we now take for granted, represents the culmination of centuries of scientific progress and the combined efforts of thousands of brilliant minds. The techniques we've developed to study Andromeda also reveal something important about the nature of knowledge itself. We can never visit this galaxy or directly sample its materials, yet we can learn detailed information about its composition, history, and future evolution. This demonstrates the power of indirect inference and theoretical understanding to transcend the limitations of direct experience. The light reaching us from Andromeda carries encoded information about stellar temperatures, chemical compositions, magnetic field strengths, and gravitational dynamics. By decoding this information, we can reconstruct the galaxy's properties with remarkable precision despite being separated from it by over 20 billion miles of space. This ability to extract knowledge from minimal observational clues represents one of science's greatest triumphs. But studying Andromeda also reveals the limits of knowledge. There are aspects of the galaxy we can never directly observe, regions hidden behind event horizons or obscured by dust and gas. The finite speed of light means we can never see the galaxy as it exists now, but only as it was millions of years ago. These fundamental limitations remind us that even our most sophisticated understanding of the cosmos is necessarily incomplete and provisional. The dark matter problem exemplifies these limitations. Despite decades of intensive research, we still don't know what makes up 85% of Andromeda's mass. This invisible component is crucial for understanding how the galaxy formed and evolved, yet it remains completely mysterious. We can map its distribution and study its effects, but we cannot directly detect or identify the particles that compose it. This mystery extends far beyond Andromeda to encompass the entire observable universe. Dark matter appears to be a fundamental component of cosmic structure, yet we have no clear understanding of what it actually is. This represents one of the largest gaps in our knowledge of the natural world, comparable to the mysteries that existed before the development of atomic theory or the discovery of electromagnetic radiation. The existence of such profound unknowns in our understanding of Andromeda serves as a reminder that science is an ongoing process rather than a completed body of knowledge. Every answer we find reveals new questions, and every mystery we solve uncovers deeper layers of complexity. The galaxy continues to surprise us with phenomena that challenge our theoretical models and observational capabilities. This open-ended nature of scientific inquiry connects to broader questions about the relationship between knowledge and reality. Is the universe fundamentally comprehensible, or are there aspects of reality that will forever remain beyond our understanding? The study of Andromeda suggests that while we can achieve remarkable insights into cosmic phenomena, there may always be deeper mysteries waiting to be explored. The potential